Okay, there we go. So I think we'll get started here. Welcome to this course on PVT and pace behavior in Whitson Plus. It's going to be a ish 50-50 focus on probably theory and at least some showing you all some stuff in the Whitson Plus software. I think it's important to emphasize that we do this very intense Whitson Plus course, which is like a half-day course where we kind of go a little bit through everything. These half-day courses that spread around the year, like these ones, they're meant to be focused on one of those items in particular. So we have 5 of these courses throughout the year. It's the PVT one, which is the first one. We have a bottom hole pressure one, which is the second one, a pure RTA focused one, a flow material balance one, and a nodal analysis one in the end of September. And the idea here is that we get half a day to focus on a little bit more in depth on theory and a little bit more in depth on applicability of a given topic, in this case PVT. I'll do most of the presentation today, but prepared all this material together with Curtis and Mo, and you'll also see that there's a few other colleagues here in the audience that's going to help with different things throughout the day. There's also 2 sessions. There's this one is the before lunch session, and we're also having one session after lunch. So we just split the group in 2, and that was just because we've had close to 150 registrants actually for this course today. The course is being recorded, so if you have to step out, if you miss something, all the recordings will be distributed after the class, and that goes for this course and all the other courses we have later today. A little bit of general information, just for those of you who, a lot of you are my friends, and we talk often, but just a little heads up, the last few, I guess, couple months, we've gotten a few new faces at Whitson. You probably know many of the ones that are existing from before, but we've got Edward on as a new software engineer, Teja, which is in the audience here today. He's finishing up his master thesis at A&M and is working for us here in Houston. And we also hired Graham up in Calgary, which many of you probably know from his Piquet days. On the course, it's a half-day course, 2 sessions, as I mentioned. The course is supposed to be interactive, so if you have any questions as we go through the course, feel free to unmute, feel free to ask those questions in the chat, and that can drive some of the course emphasis. So either in the chat or just unmute. Just make sure that you're muted when you're not talking. All the material will be distributed after the class. That includes the class recording, presentations, relevant papers, etc. And you'll see some of the slides in the slide deck is more meant for, call it presentation, and some are more meant for just reference for later. So I'll probably skip them when we get there. Everybody saw that it was sent out an email before the course. So to get software access, you simply just click this link right here, courses.whitson.com. That will bring you to a login screen where you put in your email and this password here called Shale PVT 2023. In general, I know a lot of you have become certified, but just a reminder, if you just do this 1 hour step-by-step thing, super simple on this link right here, then you just working with the software in general will be much easier. Also, working with some of the theory will be much easier. All the course material is provided here in this link right here, and if there's any other information we'll add there, that will still be added in the same link, so that'll be updated dynamically for all the participants. Also in this email, so the slides that you're looking at now should have been sent out to you, and if you're missing some of this information, just shoot me an email and I'll forward this to you ASAP. Okay. So that's a little bit of course information. A little disclaimer, this course is tailored for practitioners, so folks that need PVT properties and to understand fundamental PVT in their day-to-day work. That can be for different reasons, for reservoir production, facility design, marketing, if you're a manager, etc. So what you'll see is that the course will be of a more pragmatic character, So we try to focus on things that you can go home and apply immediately later today on data and wells that you have in your company. All the operators that's in the course today, they have access to Whitson Plus, so that is also why it becomes relevant. It's not tailored to PVT experts per se. We have another course actually this week, which is a 5-day course, advanced PVT course, that goes into a lot of depth on the things we're discussing. But that's why we have skipped for this half-day course at very advanced topics. So either topics that require a lot of details, like for instance, QCing a laboratory report, or developing an equation state model from start to finish. That is very detail oriented and will require a couple of days. Or items that lack industry consensus. So for instance, a lot of you, we can probably discuss it in a question or something, but a lot of you have heard about nanopore PVT, all kinds of bubble point suppression, dew point enhancement, etc. And we'll skip topics like that, but if you have just dedicated questions around it, we're happy to at least give you our take on those type of items. But that won't be prioritized. And we'll try to keep it practical. So what you'll see is it's going to be practical, and the things I think is important for people to know, we'll repeat it a couple of times. So some slides you will on purpose, and some topics you will on purpose see a couple of times, at least, just to make sure that we've communicated it many times. And I think about this as, when they say, when you're trying to sell a car, you have to see the car 13 times or something before you buy it. And it's a little bit the same with some of these topics. You need to see them a few times before you really understand what's going on behind the scenes. If there's any questions in the chat, hopefully my colleagues Mo and Teja that will be here the whole day can help with just letting me know if there's a question in the chat. In the digital handouts, you should have gotten all the slides that you see here. You should have got access to the Whitson Plus software, and there is some preparation material there as well. So 2 weeks prepping to this course. So 10 days ago and also this weekend, we sent out the preparation email to everyone on this email, at least if you were in the invite at that point. That had a preparation document, a very, very fast to read through. If you read through those, it's kind of like you've been fed a little seed on some of the concepts that we'll discuss today. It's also very good reference material, especially that introduction to PVT document. And for those who don't know what I'm talking about, everybody has access to this folder right here. And the first item in the folder is called preparation, and it's one called PVT for the first time. And here there's a little introduction document that was written by Curtis for AAPG, actually. So that's for geologists and petrophysicists, I think, back in '93. And it's just a very, very nice overview, 2 pages of kind of some of the key nomenclature and definitions related to PVT, some of the most important things. So if you just read through that, or you can use it as a reference. I know a lot of people put it on their walls, etc. It's a very, very condensed, simple to read document to get introduced to PVT, unless you have done a lot of that in the past. And again, this is how the folder with that's sent out to everyone looks like. Has the preparation materials, slide, some relevant formulas and definitions, some relevant papers, and an example of a PVT report. When it comes to the software, I mentioned this quickly already, but the software can be accessed at courses.whitson.com, and you'll just put in your email, and the password should be ShalePVT 2023. Okay, that's how to access the tool. If you have any issues with logging in, or any issues at all, actually, you can always send an email to support@whitson.com. The nice thing with support@whitson.com is that there is on average a 2 minutes response time. So if you have issues with logging in, getting access to the tool, if you want to talk technical details, if you don't understand the result on a well that you're working on, or if you just want to spar, Whitson support is your best friend. Again, I know all of you guys have, or most of you, at least if you're an operator, you have access to Whitson Plus. You're not supposed to use your company-specific Whitson Plus. Okay, so you should use courses.whitson.com today, because we've prepared a couple of wells for you there, and I'll go through that just quickly now. So the only thing you need to do is to go to courses.whitson.com. I'm probably already logged in, but if you're not logged in, it will look like this. So what you need to do is that you need to just put in your email, and then you need to put in shale PVT 2023, and that's it. That's how you log into the tool. There we go. So, and when you see this, you'll see see a field. In this field, you'll click the link here. I see all the projects because I'm a support user, but you will only see the project that is relevant for your users. There's 158 projects here. You should only see one project with your name on it here, and that's the one that you should click in general. Okay, that's fairly simple and straightforward. Good. The way we try to schedule the course here is I guess, organize the course is to break it down into petroleum fluids. We will not actually in detail cover fluid sampling and lab analysis, but we'll talk about PVT models and then in the end focus mostly on the engineering part. How can we use these PVT models in our day-to-day engineering? Because PVT is one of the few things, and that's also why we start with it. It's one of the few things that is an input to almost every single discipline in the petroleum domain. Okay, so this is where the focus of the course is going to be, on the engineering part, on the applicability of PVT models. But as you'll see throughout the course, we'll kind of follow this oil and gas or this PVT value chain, if you like. And at the end of the course, hopefully you can go back to the slide number 14 and see if you've been able to understand and if you're able to actually do the following. So the course goals is to make sure that we can classify reservoirs into black oils, volatile oils, near critical fluids, gas condensate, wet gases, and dry gases. Make sure that we understand the difference, and this is very important because there's a lot of confusion there, to understand the difference between in situ and reservoir representative samples. Conceptually understand what an equation of state model is and what the inputs are. Predict PVT data, that's something we're going to do many times today, from readily available data and an equation of state model that's developed for the field. Estimate PVT properties at initial reservoir conditions from an equation of state model. Calculate the original oil in place and gas in place for both oil, gas, and two-phase systems. Here we're going to probably learn a trick that some of you, or maybe most of you, haven't seen before. Hopefully it's going to simplify your life in working in some of these liquid-rich systems. And then the last thing is that we're going to generate tables from an equation state model. So at the end of the course today, you should not only be able to understand the theory, but you should be able to do all of these things yourself. So that should be something that you can revisit at the end of the day today. And again, if this was the first time you heard about PVT, go back and read this document that I referred to in the preparation material. It's an extremely good point of reference for starters. But when it comes to PVT in this course, and we'll talk about PVT as the review of physical and thermodynamic properties of gas and oil. Okay, and that's commonly referred to as PVT, as that's abbreviation for pressure, volume, and temperature. To the right on the slide here, we see the simplest, or one of the simplest relationships between pressure, volume, and temperature. It's called the ideal gas law. I think most of you guys have seen that before. It's just pressure volume equal to the number of moles times a constant and the temperature. So we'll talk more about this later, but that's the simplest type of relationship that relates these, and we'll talk about similar but a little bit more complex versions of this a little bit later. A question we get a lot here: what about water? We're also producing water, and that's correct. But just from call it a phase behavior, phase separation type of perspective, it's not as complex to deal with, but we have a slide on water and also how you can change water properties in Whitson PVT. It's a little bit simpler, so that will be the last slide we probably will go through before we do the exercises today. Before going into a lot of the details on the course, it's important that we have some basic vocabulary in place. I always go through these courses, and I think that everybody understands what I'm saying sometimes, but because I use words that we internally at Whitson use every single day. But if you don't work on PVT related items often, I can see that they can be a little bit scary and probably a little bit foreign for some of you. So the first thing we'll go ahead and do is to introduce I think 6 or 7 key kind of buzzwords that you'll hear around the course today, so that you've seen it once before we actually go into talk about it like in more depth, if you like. Okay, and the different words that you'll hear a lot is EOS model. That means an equation of state model. We'll go through this quickly. Compositions, flash, something called K values, representative samples, and solution CGR, or also known as vaporized oil ratio. So these are some key, super fundamental, call it sentences or words that we use a lot. I name drop all the time. I would say, we took that reservoir fluid, we flashed it to surface, or we flashed it at the separated conditions, or the compositions are changing. What does that really mean? So my idea here, and that just goes back from when I had my classes with Curtis in the first place. I had very little background in chemistry. I actually not have chemistry in high school. I had that in university. So I remember the first classes, every time Curtis mentioned the word composition, I forgot the rest of the sentence because I got so scared of this word composition. So the idea here is that we just go in and we take these 6 words, we introduce them for you once, and then some of them we'll introduce to you at least twice, if not more, throughout the course today. Okay, so these 6 things will be important, and maybe for many of you, at least it's not words that you deal with on a daily basis. So the equation of state model, that is just, for now, we'll just think about that as a model like any other model that has 3 input parameters. And what is actually inside of the model we'll deal with later. The inputs to this model is temperature, its pressure, and its composition. Okay? Temperature and pressure, that is things we're very, very familiar with from the kitchen. We know that water boils at 100 degrees C. We might have a pressure cooker in the kitchen. And then we have this thing that I think is a little bit scary, this composition input. But the composition is simply just the amount of different components. And a simple way to think about it, if you want to simplify your world a little bit, you can think about composition as CGR or GOR. So the ratio of gas to oil, for instance. If the ratio of gas to oil changes, the composition is changing. So when you have these 3 input parameters, you're then able to predict phase and volumetric behavior to the right here. And phase and volumetric behavior, that is formation and volume factors, it's solution GORs, it's compressibilities, saturation pressure types, it is viscosities, it's densities, it's relative volumes, etc. Okay, everything in that sphere you're able to predict with these 3 input parameters. Okay, and as I mentioned, the second term that we wanted to just emphasize in detail is this scary little word up here, at least for me, called compositions. Compositions is just the amount of different components that make up a fluid. So for instance, what makes up a dry gas is very different. That will be pure, almost only methane, versus what makes up a more black oil, which will be much more filled with C7 plus and heavy components, okay, that we'll talk much more about later. In general, it's usually expressed in terms of mole percent, and we use a little bit different nomenclature depending on if it's a total reservoir fluid, it's a vapor fluid, or if it's a liquid fluid. Okay, so we use the symbol ZI for a total reservoir fluid or well stream. For a vapor phase, we use the symbol YI, and for the liquid phase, we use the symbol XI. Okay. Here you'll also see the first time where we, with intention, are including colors to the different to the different phases, okay? And that's done on purpose. So everywhere where you see green is surface hydrocarbon liquid, okay? Surface hydrocarbon liquid, that is always in green. So stock tank oil is green, and vapor and gas phases on surface, and in general, I guess, it's colored red, okay? And that's the SPE nomenclature. And I think there's one company, maybe some of you worked in Shell before. Apparently Shell does exactly the opposite thing. But except from that, it's so in this course, you'll see exactly this everywhere we deal with liquids. We're trying to use, or hydrocarbon liquids, we try to use green. Vapor, we use red. So what is the composition? Well, a composition, if you think about it from a day-to-day perspective, if you think about air is primarily nitrogen and oxygen. So that's the composition of air. That's how you would talk about it. I love LaCroix and sparkling water. I think there's more people in the company that loves that. And that's primarily just water and CO2, right? And if you think about a petroleum fluid, the composition of a petroleum fluid is very similar. It's just many more components, especially for an oil. So an oil can actually have thousands and thousands of isomers, actually, that you can't even measure in the laboratory. But it's just a more complicated, more, complex is probably a good word, mix of many components that make up these different reservoir fluids. If it's a dry gas, it's pretty easy. It's more primarily methane, and maybe some of the non-isomer or the non-hydrocarbon isomers, but that's it. Okay, so we all have equation state model. Important input to that is the composition. We'll talk about that, how we get compositions on every single well and stuff later. So when you have an equation state model and you have the compositions, then you can do what's called a flash calculation. And I know what you're all thinking. Either you get good childhood memories from this guy to the left, or you get terrible, more adult memories from the Adobe Flash player. But it has nothing to do with either of these. So the Flash, you can think about, maybe it's fast. It's good maybe to talk about it in the context of the superhero. But in this course, when we talk about something that is flashed at a certain condition, we're referring to a two-phase isothermal flash calculation that is used for processes with vapor-liquid equilibrium. And I know there's a lot of words there. We call it VLE. But in general, where would we in general we use the word flash in a more practical context? That will be producing probably the simplest one is to produce a reservoir fluid, and you would flash it to separated conditions, and then you will essentially get the amount of each phase, so the amount of separated gas and separated oil, and you get the compositions of the different phases. Okay. So a flash just takes in a composition, let's say it's the reservoir composition, and separates it into a vapor or a liquid phase if you're inside of the two-phase envelope, right? And if you're outside, it remains single phase. So that's what flash is. Simple example here, you start with an undersaturated oil. Okay, this is an undersaturated kind of near critical oil at 0.1, that's the pressure. We have a phase envelope here to the right, which we'll talk more about. If I said that we would flash this composition at the saturation pressure, which is the bubble point for the oil, we would see a little call it the bubble of gas coming out of solution. So you will have essentially primarily a oil phase, and then you'll have a super small, what's called an incipient phase composition, which is the so-called YI. If you take the pressure even further down into the two-phase region, you'll get a bigger amount of gas and a smaller amount of oil. But you can say that you flash it, stabilize it at those conditions, it reaches equilibrium, and this is your gas phase and your oil phase. Okay, so that's what flash is in this course. So if I say flash, it just means probably most of the times I'll probably say that they have been separated at surface conditions. Very, very relevant for this, and this is a little bit important, and it's a little bit also undereducated in university. But this, according to Curtis, is one of the things that you should know about if you do PVT in the oil and gas space, because it's what you need to understand complex PVT behavior. For instance, multi-contact miscibility, and also, for instance, just retrograde condensation, and that's K values. And K values is essentially what an equation of state generates for a given composition. And once you have the K values, you can then determine the amount of the different phases. Okay, and so K values, what is that? I'll probably mention it a few times. We will need to understand what K values are to be able to explain why, for instance, the RV curve starts to go upwards at lower pressures. Okay, so K values, it's just the compositions going into the gas phase, Yi, divided by the compositions going into the oil phase, which is Xi. And this creates a ratio, right? You get a ratio that will be different for all the different components. And if this ratio just represents the relative preference of a component to be in the gas phase or to be in the oil phase. Which means if the K value is higher than 1, the relative preference is to be in the gas phase. And if the K value is less than 1, the relative preference is to be in the oil phase. Excellent example of a component that we like to have in the gas phase, that's methane. And a component that loves to be in the oil phase is, for instance, C30+. Loves to be down there below 1. Okay, and you see an example here to the right. So this is a plot that's generating K values for a given temperature. Let's say it's reservoir temperature and a reservoir composition, for instance, and you can plot the K values versus pressure. And that's what you're looking at here. So methane has the highest K values, and then as you go heavier, K values go down. Okay, so this is something we'll talk about 2 times today, and we need it to be able to understand some physics later on. Okay, so hopefully this will, say as Steve Jobs said, we'll connect the dots looking backwards at the end of the course. Hopefully, we'll see if we succeeded with that. The fifth vocabulary word is representative samples. Okay, and that's a word we hear all the time, and it's very often misused. So we just want to have a clear definition of what representative samples is. And there's 2 different types of representative samples. The first one is so-called reservoir representative samples. Okay, so that is any uncontaminated fluid sample produced from a reservoir in general, okay? And that will automatically be classified as a representative sample for that reservoir, okay? So whether it's above or below the saturation pressure, as long as it's not contaminated by any muds, which is not really relevant for unconventionals, it's classified automatically as reservoir representative. And then we have this thing called in situ representative samples. And in situ representative samples, that's a sample that's representative of the original fluids in place. Okay, so that will, for instance, be as long as the bottom pressure is above the saturation pressure, for instance. Okay, so the difference between these 2 is important to understand. And another thing we see here all the time is that, okay, let's say you have a PVT report that's recombined at the quote-unquote wrong GOR. It will be not in situ representative, but it will be reservoir representative. And a lot of people think that you can't use that PVT report for anything and that you should throw it away. So there's probably millions and millions of PVT data out there that that is thrown away because of this misconception. Okay, and here it's important for me to stress that the accuracy and the applicability of PVT data has nothing to do with whether the sample is in situ representative or not. And to try to convince you of why that's the case, for instance, when we've done the PVT study in the Permian, 150 different PVT reports. Probably most of those PVT reports are not even in situ representative, but all of them are reservoir representative. So we include all of the sample that has good quality measured data in the lab, whether it's in situ representative or not. And the reason for that is that in the EOS model development, you would like to use all of the reservoir representative samples. So whether you create a PVT model or an equation of state model, you would like to use all of them. And the reason for that is that you would like to have a PVT model that works well for all times, and not only call it time equals to 0. Okay, so what should you actually do then once, if you're on a well where you might have a composition that's not in situ representative? Well, you use the equation of state together with the other compositions you have in the field to predict these in situ representative samples, and we'll see how this is done later, but this is referred to as fluid initialization. So all of you will actually do this kind of implicitly today when we work together. So this is something we'll talk about later. So just an example to make that super clear. What is actually then a in situ representative sample versus a reservoir representative sample? So as long as the sample is producing at the bottom pressure above the saturation pressure and it's not mud contaminated, then it's both in situ representative and it's reservoir representative. If the sample is below the saturation pressure, but it's not and it's not mud contaminated, it's not in situ representative, but it's reservoir representative. And a mud contaminated sample, so that's, you know, maybe that's foreign for some people, but in conventionals, a mud contaminated sample is neither in situ representative or reservoir representative. Okay, so we like both in situ representative samples and reservoir representative samples for developing a model. The last vocabulary word, hopefully will make your life easier, is this vaporized oil ratio word, or the also called solution CGR or OGR. Okay, it has kind of a lot of names, but it's the same. And what that does is that it quantifies the reservoir gas that's in or the condensate in solution with the reservoir gas phase. Okay, so repeat that one more time. The condensate in solution with the reservoir gas phase. Okay, so what is that relevant for? Well, it's relevant for wet gases, right? Because wet gases produces a CGR. It does not have a dew point. We'll talk about that later. It will be relevant for gas condensates. And then maybe you know this, but it's a good reminder. It's also relevant for oil reservoirs. But when is it relevant for oil reservoirs? Well, it's relevant for oil reservoirs when we go below the bubble point. And why is that the case? Well, below the bubble point, gas is coming out of solution, and that gas phase, that is free gas phase, will have some condensate in solution. If it's a volatile fluid, it will have a lot. If it's a very low GOR oil, it will not have that much. Okay, but it's a very important term for you to account for this condensate in solution of the gas phase. The units is barrels per million, and the symbol. And the reason why we include both here is just to make sure we're SPE compliant. SPE uses little rs when referred to as that solution CGR or OGR. So that's just condensate gas ratio or oil gas ratio. And in the industry, well, what you'll see in Whitson Plus, Eclipse, ResFrac, all these different tools is typically RV, which is capital RV, which refers to the vaporized oil ratio. Okay, and we'll use the terms interchangeably within this course, and you will see the definition of this a little bit later. Okay, now we should be ready to rumble, and I was wondering if there's any questions at this point, or doesn't look like it, so that's good, I guess. We'll just fire. So I think now we have some of the basic vocabulary, which is important to understand. Also some basic concepts, and we can now narrow the discussion a little bit towards shale PVT and really what makes shale PVT different from, call it, conventional PVT. So like in an offshore field or a conventional onshore field with much higher permeability. So the four characteristics of shale PVT, or what you see in basins like the Montney and Duvernay, Bakken, Anadarko Basin, Powder River Basin, Eagle Ford, Austin Chalk, Permian, etc., is kind of these four things. Maybe there's some exceptions, but in general, we see that most of these basins, they span a wide range of fluids, from low GOR to high GOR. Okay, Eagle Ford and Montney, it's probably the most extreme ones there. Very low GOR oils all the way up to dry gases. Permian, a little bit narrower. Bakken is probably the exception here. But okay, most of the basins span a wide range of fluids. The basins have areas, in most cases, that are slightly undersaturated or actually saturated in situ. And we'll talk about what that means. Well, that means that you're either very close to the bubble point or dew point, or you're actually below the saturation pressure from the first dye you start to produce. And that makes it very complex sometimes. The third thing, which is unique for unconventionals, is this rapid decline in bottom hole pressure. And that's not something you see that often, at least in conventional fields. Okay, and that has to do with a very, very low perm in the way we develop these fields. And the last thing is how, what kind of is difference between a conventional well and an unconventional well will be that the producing GOR is a strong function of the flowing bottom hole pressure when you're below the saturation pressure. While in a conventional field, it will be actually a function of the average reservoir pressure. And we'll talk about why a little bit later. So just to remind ourselves that these things are true and that these are kind of the characteristics, and we should have this in our mental model and in our kind of mental toolkit, that these things are true. We can start with the first one, that shale basins span a wide range of fluids. That is true in every single case except on Bakken. Here we see just Eagle Ford tilted and Montney tilted, just an example. Oil, wet gases, and dry gases, and condensates and everything in between, and very critical fluids and whatnot. Okay. The second thing that I talked about is this, that most of the basins have areas that are slightly undersaturated or saturated in situ. So we've done these PVT studies in all of these unconventional basins, right? With all these multi-client studies. Biggest one is the Permian, but many of them are really big, where we have initial pressures and we also have saturation pressure ranges in those basins. So if you compare the initial reservoir pressures with the saturation pressures in the basin, you will see that there's some overlap in every single case, maybe except from the Bakken. What that means is that you'll have areas in these different basins that have a saturation pressure or bubble point that's very close to the initial reservoir pressure, or even actually higher than that. So GORs shoot up immediately, and you're actually dealing with a very, very complex three-phase problem from the get-go, and that is very interesting in a lot of these basins, and it also makes it very complicated. And it makes it particularly complicated because of the bottom hole pressure that changes so fast. And we talked about this as the third bullet point. And just to remind ourselves that this is true, just have a quick example here. This is the bottom hole pressure versus time for Eagle Ford well, I think, that we presented a few years ago. And you see how the GORs essentially here, this is Eagle Ford well, basically shoots up from day one. So it's very close to either being a little slightly undersaturated or saturated in situ. And GORs increase immediately. So it can actually be extremely hard to sample in so-called in situ representative fluid sample for this particular well. And what we've done here is to predict the well stream compositions every single day. And then we just ran a saturation pressure, so a dew point or a bubble point calculation. And you actually see here that if you sampled after 70 days for this well, and you brought that to the lab, it would predict it to be a dew point, versus early it will be a bubble point well. So it kind of almost changes phase, if you like, through the lifetime of the well. So we know that that's true. And the last thing is this thing about unconventional well performance. And this, I think, is relevant not only in the PVT space, but is also relevant from an RTA perspective, for all of you who do that, or just well performance in general, is the producing GOR in unconventionals. It's of course, as in conventional reservoirs, it's a function of the initial GOR or your composition. That's given, but it's also a very strong function of your flowing bottom hole pressure. Okay, and that's very characteristics when you're in infinite acting flow or transitional flow. Okay, and then it's also a function of all these other things that I'll just skip, but those are the same as in conventional reservoirs. But it's different than a conventional reservoir, because in a conventional reservoir, the GOR is a function of the average reservoir pressure, and that has nothing to do with the fact that it's conventional, but that's just the way GOR behaves when you're in boundary dominated flow, actually. And in conventional reservoirs, you're much more in boundary dominated flow than compared to an unconventional well. Okay, so that is a fundamental well performance difference between unconventionals and unconventionals that are PVT related, if you like. And a cool thing, you have Whitson plus, you can create a synthetic case of a case that goes straight into boundary dominated flow, and you can plot the GOR versus the average reservoir pressure and the flowing bottom hole pressure, and you'll see there's a strong trend there. And you can do the same for just a low perm system and see that it's a very, very strong function of the bottom pressure during infinite acting flow. But these things are great. We know that this is true. We just want to make sure that we know, what does this imply in general for us as engineers? And what it implies in general, and what you will observe on all of these wells, is that the rapid decline in bottom pressures, the complex fluids that we observe in many of the basins, results in a rapid change in produced fluid properties. So we have a changing GOR and a changing stock tank API that just changes extremely fast. Your produced compositions are changing extremely fast in these unconventionals. And to remind ourselves that this is true, just another example, and this will look like this for every single well, but here we've just tracked the C1 and C7 plus content over time for a well in the Eagle Ford. I think this is just the first year, and you see it goes from around 40% methane all the way up to close to 65 just over the year of the well. So we know that the compositions are changing a lot. So if the CGR is changing a lot, the compositions are also changing a lot in the same period of time. The last thing that makes unconventional fluid systems very unique in general is the fact that they exhibit a very, very strong field-wide fluid consistency or thermodynamic consistency. And what does this actually mean? It sounds like, okay, Matthias, you're saying this, but I don't believe you. How can I quantify whether it's consistent or not? That's an excellent question. But what it means in practice is that the relationship between molecular weight and specific gravities for the heavier components is very, very strong. And you can plot it. For instance, if you plot stock tank oil, for those of us in the Permian JIP, for instance, doesn't matter what formation, doesn't matter what part of you're on the Delaware or Midland side. If you plot the stock tank oil measured molecular weight versus API, it's a straight line. And we had a few outlier data points there that was from another basin, and you see it's a very, very different line. And that kind of consistency was a very surprise for us to find in essentially every single unconventional basin that we've been working on. What that results in is that PVT properties are highly correlatable across a field or a basin. So that allows you to use one fluid model, so one equation of state model for the entire basin. And we haven't talked much about this already, but we'll talk about it here a little bit later today. What is in a fluid model? What does it look like? Why do we care? Etc. But this is the reason. I'm not a geochemist or anything like that. Of trying to explain you the reasons why it's so consistent. There's been a few attempts in the literature explaining why it's so consistent. One is from Equinor that showed all their work in the Eagle Ford. This is just a little snippet from that paper saying that PVT correlations demonstrate strong field-wide consistency, although the reservoir fluid, which is the compositions, varies significantly. Okay, so reservoir fluid composition, that's GOR. PVT properties can be estimated from one key parameter, this is GOR, and this contrasts from reservoir fluid complexity in conventional reservoirs. In conventional rocks, due to relatively high permeability, fluids migrate within the reservoir with a complex charging and mixing history. The fluid mobility in shale reservoirs is much slower, reflecting the dramatically lower permeability. Fluid communication and migration is limited, and reservoir fluid differences are dominantly determined by thermal maturity, which is the main reason behind the consistent PVT trends and correlations over large areas. Okay, so the question that arises then many times is, okay, if it's so consistent, why can't we just create one PVT model for all the fields? And that's an excellent question as well. But the answer to that is what is actually different between Niobrara to Eagle Ford and Scoop Stack, for instance, is these heavier components. So that's how we characterize everything that's heavier than C7 plus. And why that matters is if you take C14, for instance, C14 can have up to 1,800 isomers a part of it. So your job as an engineer or the engineer that develops the fluid model, they need to try to capture the average C14 in the basin. And that average C14 is very, very linked to whether that fluid is more paraffinic or less, or more paraffinic or more aromatic or something in between, which is called naphtanic, and we'll talk about that later. And this is related to C7 plus characterization, and that's something that is very important that we'll talk about in a second. I don't think there's any questions, so that's great, but just shoot if you have any. Okay, so over to the fundamentals of PVT. Many of you know and heard about PVT, and it's one of the very few things, it's probably the only thing that I can think about that has an impact on essentially every single discipline in the petroleum domain, whether it's implicit or explicit. Okay. So whether you do reservoir simulation, whether you do well testing or RTA, whether you do pipe flow calculations, process and facility design, reserves, also drilling operations, you name it, all of it is PVT. Okay, densities is PVT. So you need those properties for a wide range of activities. And it kind of makes sense if you think about it. Like an oil and gas company sells oil and gas products. And what is PVT? Well, PVT is what tries to explain how oil and gas behaves at different pressures and temperatures, all the way up to stock tank conditions where it's being sold. So it makes sense. A key concept when it comes to PVT, though, and this is very important for what we're going to do later, is that a barrel is not always a barrel, or a cubic meter is not always a cubic meter for our Canadian friends or our Norwegian friends as well. Okay, and what we mean by that is, if you think about PVT, if you think about the volumes in the oil and gas industry, it's actually very rare that you see, it's not only a volume associated to it, but it's also a context. Okay, so a reservoir barrel is not equal to a separator barrel, and it is not equal to a stock tank barrel. And what we mean by not the same is, of course, the volumes are the same, but the amount, the densities, the composition, and the monetary value of each of these are different. Okay, so a reservoir barrel of oil shrinks to the stock tank, and then it shrinks even further it's to separator and even further to stock tank. And this is very important for you to understand. So you'll see in the software on purpose, we're very clear about that. We're very intentional about the use of reservoir barrels where reservoir barrels should be used, separator barrels where separator barrels should be used, and stock tank barrels where stock tank barrels will be used. You'll never in a single place in our software see the use of just BBL and no context. It's always STB if it's stock tank, and if it is separator barrel, it will say SEP dot BBL, and reservoir barrel will be RB. And that's with purpose, because it is very important to know the context. The second thing about PVT, which maybe some of you know, but maybe for some of you it's not as clear or you haven't thought about it, is that PVT properties is actually process dependent, or they're path dependent. Okay, so if you're producing from some kind of reservoir, the final product volumes, also how much you produce in terms of liquids, they actually depend on the pressure and temperature conditions from the reservoir to sales and the path that they got there. And in short terms, it means that GOR and formation volume factors are process dependent. So what does this mean, Matthias? Translate this into layman terms. So I'll try my best, okay? So if we have a oil barrel to the left here, and we produce this oil barrel through a super complex processing system, a gas plant here at the top, and we get a certain volume of gas and oil, that will be different than if we flash that straight to stock tank. If we take that, no processing, we just separate it at stock tank conditions, we get a gas phase and an oil phase. And it will also be different than if we, for instance, have a test separator at the higher condition than stock tank conditions, okay? So in this case, you'll see the complex processing. That's why we have more separators. That's why we have complex processes facilities, to be able to get more valuable products out of the same amount of components, okay? So a complex system should give you a lower GOR. In this case, the GOR should be 8,400. And the GOR of the single stage flash is around 9,250. So that means that, you know, your information volume factor in this case is higher for this case, and you would like that to be as low as possible typically, because you get much more value for your liquids than your gases. And that's, nothing else has changed. It's the same wellbore. The only thing that's changed here is how we process it at surface. And then here also the context comes in and becomes very important, because if we measure the GOR of the same fluid, same composition, we just measure it not at stock tank conditions, but at the different context, which in this case is separated conditions, we get in this case 6,700 scuffs per separator barrel. And then when you flash this down to stock tank, this will most likely be a number between 8,400 and 9,250. Okay, because it's a two-stage process. So think about that for a second. Awesome. Okay, so first question now. First quiz, and everybody needs to write in the chat here now, just after they thought a little bit. Here we're looking at a reservoir fluid, and the reservoir fluid has a lot of gas. This is the mole fraction over time, and you need to, in the chat, write what you think this fluid is. Do you think it's a reservoir oil or a reservoir gas? And I'll start, and I think it's water. No, that's a joke. But just write what you think it is in terms of reservoir gas or oil in the chat, just after you've looked at this. And just for simplification, this is light. This is call it gas. This is intermediates. This is heavy fractions, and this is the distribution of the heavier components. Yeah, good that we get a few different questions, a few different answers here. Great. Okay, great. It was like super liquid frequency. Okay, that's great. Still see that we're missing a few. Just shoot, there's nobody. This is just a good way to activate a little bit, think a little bit. Do we think it's an oil or do we think it's a gas? It's 50-50. Okay, great. Great. Excellent. So, okay, so we have a lot molded mud. That's in theory, might some of the components, we don't know. Maybe there's mud there as well, Mo. So it's not a bad guess. But obviously, this is a kind of trick question. What I mean by that is it looks, if I was going to look at it, oh, Logan Brown, that comment right there, it's beautiful. So if nobody saw Logan's comment there, depends on reservoir conditions. And actually, that's a super good point, that the reservoir temperature would matter here. But for most physical, where oil and gas originates in that pressure or in that temperature range, it would always actually be an oil, this guy right here. If this was going to be a reservoir gas phase, it would have to be, 7, 8, 900 Fahrenheit, which would be. So that's a super good point from Logan. So it depends on reservoir temperature. We'll get back to that a little bit. And I was actually hoping some of you would mention it, but that's beautiful. But it is actually a reservoir oil. And the reason why this is a trick question is that I showed you the mole fraction of each individual component here. So that's why a lot of you answered gas. But if we go in here and we convert this into mass, okay, so we have number of moles, that's just a number of components, I guess. And then if we convert this into mass and we do the same quiz, if I've asked you guys now, in terms of mass fraction and not mole fraction, is this a oil or a gas? And I'm pretty sure all of you would have said it would be an oil at this point, because if something is on a mass basis, 78% made out of that of the stuff that makes it an oil, basically, which is C7 plus, then you would probably think it is an oil. At least I would. So this is actually just a trick question, but just to activate you a little bit later, we will talk about some very rough rule of thumbs when it comes to this, so that it will be easier for you if you knew that. But the whole point about this exercise is a key thing to understand here is these components that are heavier than C7 plus. And I mentioned that already once, that what is different between Eagle Ford, Niobrara, etc., that is the components or the C7 plus characterization. And here you see the C7 plus characterization, or the C7 plus close mass fraction, is also very important to distinguish what kind of reservoir fluid it is. Okay, so very key to understand PVT is the heptanes plus part. We call it heptanes plus characterization or C7 plus characterization. Okay, and it's very, very correlatable to different reservoir fluids. And Equinor put together a very good summary of all of their fluids from high GORs to low GORs. This is again just rule of thumb bracketing. You know, a dry gas should probably not even have any C7 plus, but here we are, you can kind of bracket it into two different regions here. We made this into a little nice table if you're interested in that. And again, these are just rules of thumb. And why are they rules of thumb? Well, they're rules of thumb because of that beautiful comment from Logan about reservoir conditions, because there's no information about the reservoir temperature here, right? We'll talk about that later. So these are only rules of thumb. What SB has out is rules of thumb. What Curtis, my boss, has out is rules of thumb. What we have here is rules of thumb. McCain is rules of thumb. And in the end of the day, what dictates what the fluid is if you take that fluid at the reservoir temperature into the laboratory, or you model it with an equation of state, and what it exhibits there in terms of dew points or bubble points or nothing, that is what dictates what fluid it is. These are just rules of thumb and nothing else. So you shouldn't use this to rigorously, at least if you have PVT data, to classify your wells. Good. So hopefully we learn a few things about C7 plus characterization now, which is good. And at this point, the clock is 9:01, and we'll take a 15-minute break. So we'll be back at 9:15, and we'll get a little bit more into the weeds here. Okay. With that, I'll just mute myself, and we'll be back in 14 minutes. Okie doke. So we'll get started again. I saw Cody. I think we had to add you manually, but not in like the bulk upload. So I think you should be good now on with the project. If anybody has any other issues with seeing their project in the software, just let Mo and Marcus know in the chat there, and we'll get to it ASAP. Next topic now is reservoir fluid classification. That's a very important toolkit to have in the back of your mind. And in general, when it comes to reservoir fluid classification, we like to distinguish between primarily 5 different reservoir fluids, and this is just kind of typing, right? Primarily, but it's important to understand. And it's dry gases, wet gases, gas condensates, volatile oils, and black oils. Sometimes that's a little bit of a diffuse, call it definition to some degree, but between gas condensates and volatile oils, it's something that we sometimes just call near critical fluids, NCs, okay? And that just means that the pressure and temperature is very close to the critical point of that fluid. And what is the critical point? Well, the critical point is the point at which the properties of oil and gas essentially converge and they're equal. So you can't really distinguish whether or not it's a liquid or a gas. Okay. So just if we talk about near critical fluids, that's between here, and we'll give you kind of an example of that later. So the classification itself, though, is something that, at least when I saw it the first time, I was a little bit surprised on how we did it rigorously. Okay, so this is how you do it rigorously, not with these rule of thumb tables that I showed earlier. So there's 2 things that we use to classify the reservoir fluid. The first thing is the location of the reservoir temperature with respect to the critical temperature in the Cree-Connon term. And it's also the location of the first stage separator pressure and temperature with respect to the phase diagram of the reservoir fluid. And this part was a little bit non-intuitive to me in the beginning because, you know, this item right here, that is a surface item, right? It's the surface separator conditions. And why should that really matter for a reservoir fluid? Okay. We'll take a look at that and see how it impacts what a reservoir fluid can be in terms of classification here in a bit. But what we'll go ahead and do is to look at black oils first, which is kind of the simplest one, what we learned about in school. We'll look at volatile oils, condensates, wet gases, and dry gases. We'll look at that from the lens of just a phase envelope. Here, we'll start with the black oil case. We see that this is what we call the Cree-Connon term. This is T crick, and then this is what we call the critical point. That'll be TC, and in general, so this is T crick. A little bit bad at writing here, but we're to the left of this item if we're dealing with a black oil. So for a black oil, in general, we're far away from the critical point. The critical point is here, so that's when we transition from a bubble point to a dew point. Far away from it here to the left. And if we plotted the so-called liquid relative volume, or the shrinkage below saturation pressure, you will see that the saturation pressures are relatively low, and also the shrinkage will be relatively linear. So there's no curvature to this line. Okay, and that will be the difference between a black oil and a volatile oil, at least internally in our shop. Okay, so we're far to the left of the critical point, and we're exhibiting a bubble point when we reduce the pressure. Okay, so green for oil. A volatile oil, we're closer to the critical point now. Over here, right? That's TC, but we're still not on the condensate side, so we exhibit a oil, so it's liquids. So if we plot the liquid relative volumes, it's 100% liquid above the saturation pressure. But if we look at the shrinkage curve, because it's so volatile, the shrinkage curve has more of a bend to it. Okay, and that bend to it is kind of the signature if something is more volatile versus black oil. And On a rule of thumb basis, this happens around 1,000 scuffs per barrel. And we'll talk about that later. So this is a volatile oil. And when we get to retrograde gas condensates, we're between basically this critical temperature right here, which is TC, and the Cree-Condon term. So we're between these two guys right here. And when we reduce the pressure, we see a dew point, and of course above the saturation pressure here, there is no liquid. So when we plot the liquid relative volumes, there's no liquids, and as we go below the saturation pressure, liquid is coming out of solution, and the liquid relative volume drops. Then it actually flips and turns non-monotonic, and to be able to explain this, we need to know our K values. So you'll have a condensation-driven period and a vaporization-driven period. And this is what you'll see for the first time now. And later we'll use it to explain why the RV curve looks like it does. Okay, so that we'll get back to that. But so it has a little bit different shape when it comes to the liquid dropout curve than, for instance, the oil case. A wet gas is essentially a fluid that has no dew point at reservoir conditions. So we're to the right of the Cree-Condon term. So when you reduce the pressure at reservoir conditions, it has no dew point. And then when we bring that fluid to the surface separated conditions are inside of the two-phase envelope. Okay, so that means that there's no liquids in the reservoir, but at surface you have a gas phase and a liquid phase. So that's a wet gas for you. And the wet gas has no liquid whatsoever, so liquid relative volumes are zero. That's simple. And what's the difference between a wet gas and a dry gas? Well, the difference is fairly small, if you like, but it's basically just that there's no dew point at the reservoir conditions, and also the surface conditions are outside of the two-phase envelope. Okay, so there's no liquids, hydrocarbon liquids being produced at the surface. So if you lowered this pressure, or for instance, lowered this pressure or temperature such that you were actually inside, you could actually change, call it a dry gas definition well into a wet gas definition well by just changing the surface conditions. And that's been done before. I think there's like a legendary kind of Texas story about what I think they were called the White Oilers, and they to make sure that they could classify the well as an oil well, they put a freezer or refrigerator on the wellhead, which was actually a gas well, and they produced basically what looked like transparent white liquid or white oil essentially, and they used that to have a different spacing than if it was a gas well. And if Kurz was here, he could probably take that story much better than myself. But or main point here is that it really matters what your surface conditions are, and we'll take a look at that now in a sec. But to summarize, a volatile oil well that starts near to the critical point. As it goes below the saturation pressures, gas bubbles rise or form and rise, and as you stabilize at some lower pressure, you'll have a gas phase and an oil phase. So it's 100% liquid, gas bubbles form and rise, and you get a gas phase and an oil phase. For the condensates, it's the opposite that happens. So if you're on this side of the critical point, you start with 100% gas. As you go below the saturation pressure, droplets are forming and falling, and you're getting a gas and an oil phase. Okay. And just to show you a quick example of this in Whitson Plus, I'll just do call it the reservoir fluid example project here, and just show a few different just for that you can create all of these different fluid systems in Whitson Plus, for instance. So if we just do something simple, you don't have to do this. I'll just show you real quick. So if we deal with a 500 scuffs per barrel type of fluid, you'll get of course your phase envelope and everything will change. So now you see this is a so-called black oil fluid, and we're far away from the critical point. And if we go to the black oil table feature here, we'll do this together later. You'll see that the GOR is 500, the formation volume factor is 1.2. The black oil classification is now set to a black oil, which you see here. And you'll also see the solution GOR curves and the formation volume factor curves. They're fairly linear as you go below saturation pressure. If we start to add more gas in solution, let's say we do 2,500 type of fluid instead, we'll have a much more volatile system. So now we'll be talking about a volatile oil. The equation of state behind the scene is the same. We're just changing the composition. We'll talk about this later. That's the only thing we're changing. Now we're seeing where our reservoir conditions is closer. I mean, the reservoir conditions are the same, but it's essentially the reservoir fluids critical point have shifted more to the left, so we're closer to the critical point here. And you see also now on the solution GOR, there's more of a bend to it, also on the formation volume factor curves. And the classification now is a volatile oil, and also the bubble point are typically much higher in general because there's more gas in solution. If we take this one step further and makes it very near critical, if I try like 4,000 scf per barrel, for instance, that's kind of my go-to rule of thumb. That's around 250 barrels per million. Then you see we're getting very, very close to the critical point. Just for fun, can we see if we maybe make it even closer? Maybe this will flip it to a dew point. But that's essentially what you would call a near critical fluid. So this is actually a near critical gas condensate. The other one was a near critical black oil. And you see now the reservoir conditions are essentially just above the critical point right here. And I think this is a gas condensate, but a very near critical gas condensate. And you see as we go below saturation pressure here, the formation volume factors and stuff are not only volatile or like curvy, they almost go straight down in the beginning, which is kind of a signature of those type of systems. And as we increase our GORs, let's say we go up to 10,000 scf per barrel, that's around 10,000 scf per barrel. That should be around that's 100 barrels per million. Then we're dealing, of course, with a gas condensate, and as we can change the method actually in Whitson Plus, which we'll all do later. If we change it to a more of a wet gas system, I think that will be what we'll probably get here. That's actually not wet gas, but as long as we have a GOR in the system, let's say the GOR is 100 or 200,000, I think we'll probably get there and get a system that is close to. Oops, I don't know if I did that correctly. Yeah, there we go. This is more of a wet gas system right here. So there's no saturation pressure. The phase envelope right here does not intersect with the reservoir temperature or with the reservoir temperature right here. But we see we're inside of the two-phase envelope at this point, and we're getting a GOR around 200,000 barrels. So what's the difference between that and a wet gas? If we did like a wet gas specific gravity of 0.6 or something, I'm pretty sure, yeah, there's basically no even phase envelope. It's so dry, the stuff, primarily methane, a little bit of these lighter components in this case, and we're dealing with a dry gas right here. Okay, so that was just to show you, like, all of this is essentially generated with the same equation of state model, just different fluid types. What is actually changing is the composition, from low, in this case, the low GOR fluids to higher fluids. What you saw now when I was clicking this button, and all of you guys will do this later, you'll see the composition as predicted by the software for this particular fluid. And that is related to the next topic called petroleum fluids, okay? And petroleum fluids is, at least you can group it kind of a little bit simplistically into paraffinic fluids, aromatic fluids, or something in between that we call naphthalenic. And in general, they're made up by what we call alkynes or paraffins. In terms of structural formula and shape, they look like this. I'll not spend much time on it. You have naphthanes, such as cycloalkanes, and you also have aromatics or aromatics that look like this. Examples are benzene and toluene, for instance. So that's kind of some of the key groups, and the way to classify which of these groups you typically will call it be under. You can use what's called the Whitson characterization factor. The Whitson characterization factor is the first thing that a lot of people in our company, when we work on a new field, calculate for a fluid in a field. It's very simple. You take the molecular weight and the specific gravity of that fluid, you plug it into this formula, and you'll get a number between 8.5 to 13.5. And then if it's a paraffinic fluid, that will be between 12.5 to 13.5. An naphthalenic compound will be 11 to 12.5, and an aromatic compound will be 8.5 to 11. So it's a very easy way to kind of group, okay, what family of hydrocarbons are you looking at? We have not done a lot of work in Uinta Basin yet, but we're starting to work with some companies there, and they're kind of known for having a peanut butter type of fluid, and that peanut butter type of fluid will be very, very paraffinic, so that will probably have a higher Watson characterization factor. Most of the unconventional fields we're working at, they have a K-value or a Watson characterization factor of around 11.5 to maybe 12.5, so it'll be more in an naphthalenic range. And when you plot that on a graph, it looks like this. And if this trend is consistent for a basin, which it is in at least all the basins we worked on, if you're either on a trend like this, or if there's another trend that is very consistent across the basin, that's an excellent thing. That just means that the basin is very, very consistent from a paraphenicity-aromaticity relationship. We also have non-hydrocarbon compounds in the mix, so that's found in most of the reservoir fluids. CO2 and H2S, they're unwanted most times and costly to deal with, unless you want CO2 for injection in some kind of a case. And then nitrogen is typically also not wanted because it reduces the heating value of the gas. So typically these things will always be there to a bigger or smaller degree, and they typically have negative impacts. At least it will be more costly. So when you go out to measure a composition in the laboratory, you'll have a mixture of these non-hydrocarbon compounds and these hydrocarbon compounds, if you like. And that will look like something like what you see to the right here. To the right, you'll just see the molecular weight of the individual components and the components. And typically it's the same for all the, or most of the different laboratory reports. So if you've seen a laboratory report, you'll see that you have the non-hydrocarbons, then you have some pure compounds with known molecular weights, up to C6, and sometimes you'll have isomers as well, like benzene and toluene, and then you'll have single carbon components. And just for reference, if you are in conventional fields where you have mud gas contamination, C12 to C20 is where you'll have that mud contamination. To the right there, just to show that these are the non-hydrocarbons. These are the pure compounds. Those are the compounds that everyone knows. In every textbook in the world, you will see that methane has a molecular weight of 1604 grams per mole. That's the same all over the world. That's what it is. The problem is when you get into like C12, the C12 molecular weight, the fact that it says here that it's 161, that's just from some kind of correlation. That's not true for all the fields. So for a field, you need to find the actual molecular weight for that field. So this is a mix of isomers and single carbon numbers, and these are the single carbon numbers, and they're just estimates. Okay. Very important to emphasize here when it comes to the measurements of these fluids in the laboratory is when it comes to the compositional measurement. So every time we're involved in these projects, people think that just because it's coming from a laboratory where they've measured the compositions, that the compositions has no uncertainty through it. That's like, okay, this is what they measured, and so that's what Mother Earth gave us when it comes to this fluid. This is the fluid composition of that fluid. But like any measurement in general, all measurements are subject to interpretation and is also subject to uncertainty. And if you actually talk to the labs, if you actually go and visit a lot of these labs, what you'll see is that the most uncertain type of measurement, or one of the most uncertain, is actually the compositional measurement itself. So that's something to be aware of. And I'll give you the short answer of why it's very uncertain. So when you are in the laboratory, you use a so-called GC tool, and the GC tool measures not the mole amount that you need for your calculation, but it measures the mass amount that you need for the calculations. So that's the first thing. So you will basically get a number of weight fractions of each individual component that is then converted to moles by using the total sample's molecular weight and the individual component's molecular weight. And the way to do that is just to apply this formula right here. So if we look at this, the weight fractions themselves, they can be uncertain because of baseline shift issues, or that an internal standard hasn't been applied appropriately, for instance. so that there's uncertainty in the direct measurement of this. And it's also the total sample's molecular weight. The way to do that is to use the so-called freezing I think it's like benzene freezing point suppression method. And to do that, you get an uncertainty of around 5 to 10%. And then these molecular weights of the individual components, for a pure compound, it's known. For a single carbon number, it's estimated. And for the heaviest components, it's extremely unknown. So you see there's uncertainty here, there's uncertainty here, and there's uncertainty here that adds up to a number that you should be able to, or at least not to trust at face value. You should have some tools to be able to evaluate whether this composition is a good composition or not. And for all of you guys that have worked with us in these JIPs, had meetings with Bilal, Curtis, Singh, Sissel, Ahmad, etc., they go through that and how we evaluate if a composition is quote unquote good or not, and how we deal with that laboratory uncertainty in the compositions. So to the right here, everything here is known. In terms of molecular weight, these are estimated. So that's kind of good. Anyways, so enough compositions already, Matthias. That's probably the most in-depth on compositions. But related to compositions is kind of like for some of you, NGL, LPGs, and LNGs can be a little bit confusing sometimes. What is actually the difference? Well, liquefied natural gas is primarily C1, LPG is primarily C3 and C4. NGLs is natural gas liquid, so that's typically C2, C3, C4, and C5. And then crude oil will typically be everything that's heavier than either C5 plus or C6 plus, roughly speaking. And in a daily, what do we actually use these things for in our daily life? Methane we use for heating, ethane for, can be plastic, for instance. Propane is mainly heating. Butane is heating and cooking. C3 and C4 is sometimes used for auto gas in some places in the world. And then C5 plus is primarily what we put in our cars or in our planes, etc. Okay, so that's compositions for you. So when you read a composition, we'll take a look at the PVT report a little bit later. That there's uncertainties associated with that you need to account for when you create a PVT model, and that is the next topic. Any questions here, or are we? I think we're good. Perfect. So now we're getting into the more things we need to know about in our day-to-day work, and that's PVT models. Because every time you do an engineering calculation that's physics-based in any domain that we talked about already, you need a model that describes the relationship between pressure, volume, and temperature for different fluids produced from a basin. And all engineering calculations, they require the following for a given pressure, temperature, and composition. We need the amount of each phase, we need the density of each phase, and we need the viscosity of each phase. There's two different ways to model this in the oil and gas industry, and that's with a compositional model, a so-called equation of state model. And that is every single calculation we did now was with this equation of state model right here that we were running in the background right here. Okay, so this is an equation of state model that's been used to fuel all our calculations right here. But with that equation of state, we predicted a composition. That composition automatically created a table, and that table is typically what is actually used in the exact different calculations that we're applying. Okay, so we have a compositional model, and typically the compositional model in 99.9% of the time is not used directly, but we use derivative products of that model, which is typically delivered in terms of a black oil PVT formulation. And that's what the two models we're going to talk about. So one of the course goals was that all of you should be able to, at least on a generic basis, be able to explain what an equation of state model is. And to be able to understand what an equation of state model is, and an EOS model, we like to use just a tank model as a base case for that. So think about, you have a tank with a particle inside of it. Everybody knows back from university that pressure is defined as a force divided by area. So in this case, the pressure is defined by the average force on the tank wall by this particle. Okay, so every time this hits a wall, that's kind of what builds pressure for this tank. So in this tank, we have 4 different particles here right now. They're moving around in the wall, and they exhibit some kind of pressure on on the, or call it force/pressure on the tank wall. If we went in here and we doubled the speed of the particles, we'll be hitting the wall twice as many times and increasing the pressure. Okay, and that will be our analogy to increasing temperature. Okay, so we know that increasing pressure and increasing temperature should be correlated. If the temperature or if the speed was the same of the particles, but we doubled the number of particles, what will happen is that we'll hit the wall twice as many times. So the pressure should go up if we increase the number of moles or the molar amount. If we keep the number of moles the same, the speed the same, but we just increase the volume, we'll actually see that there's further away from every time we hit the wall itself. So the pressure will actually go down. So we know there's an inverse relationship between pressure and increasing volume. So the observations that we made is that the pressure should be correlated with temperature. We know that pressure is correlated with number of moles. We know that pressure is the inverse, has an inverse relationship to volume. And the result there is essentially what we know as the ideal gas law. And why do we start with the ideal gas law? Well, the ideal gas law was one of the first equation of state models that we had in the industry. So it was introduced back in 1837. And a few years later, we had this guy called van der Waals. I think he won the Nobel Prize in Chemistry for this equation, van der Waals equation. And that was just a little bit more advanced version of the ideal gas law. And then around 100 years later, in the 1970s, we developed basically oil and gas specific versions of this van der Waals equation that we refer to as SRK or the Peng-Robinson equation of state. There's two different versions that we use in the industry today, and that's the industry standard equations of states that's used. They're used in 99.9999999% of the times. Okay, if you're using an equation of state, either of these two. Both of them are so-called cubic equations of state, which means that if you rearrange the equations and everything, you'll get something to the third, and then something to the second, and something to the first, and then some kind of constant, right? So that's what's called a cubic equation of state. Their predictability is identical. There's none of them that are really better than another one. I think you can even convert one to an equivalent of the other. Why do we have two? Great question, and many times it's just because of tradition. So SRK got very popularized among the process community in the 70s, and Peng-Robinson became very popularized among the reservoir community. And then when both of us started to kind of work together with the integrated asset models and yada yada, we've kind of just decided to keep both. But we, for the most part, just use Peng-Robinson because there's, at least when it comes to simulators, there are more simulators supporting Peng-Robinson than SRK out of the box, and also in a little bit more consistent way. But it doesn't matter which of the ones that you like to use. Again, an equation of state model that can be either of these two, just pressure, temperature, and composition, and you can predict PVT properties. If I asked, for instance, Logan here earlier, which is a great comment. If I asked Logan to send me, Logan, can you send me the equation of state model for this basin? What would he actually send me? How does it actually look like, this model inside here? Well, it would always be either the Peng-Robinson equation of state, or it would be the SRK, or the SRK equation of state. So either of those two, and both of them, no matter which of them it would be, they would be represented by two tables. So the two tables, that's component properties, and the other one is binary interaction coefficients. The component properties has a lot of information that we learned about in high school: molecular weight, critical pressures, critical temperatures, and a few oil and gas specific values like eccentric factors, volume shifts, critical C factors, etc. And then binary interaction coefficients is something else. These two tables, that is what represents the model itself. In a field in Whitson Plus, you'll see that there is always one primary equation of state that's used for the field. If you click it, you can look at it and export it to any third-party format, and you'll see that there's a BIPS matrix here there's also a component property matrix here. And just an FYI, this equation of state is just actually a default Ping-Robinson equation of state. And the reason why Permian is added here at the end of the name is just because the field is called Permian, but it's just a default equation of state for, or Ping-Robinson equation of state in that case. So when it comes to a lot of the work and a lot of the reason why we've worked with a lot of you companies is that we've done these PVT studies in every single basin, where we've gone out and taken all the PVT data from all the relevant wells that have PVT data from a wide range of companies and from a wide range of laboratories. The wide range of laboratories is actually extremely important because every laboratory has different ways of calibrating their equipment, and you want to make sure that you're not calibrating to some kind of lab bias. So it's really good that we have many different laboratories, and also companies and vintages, and probably also even laboratories within the same companies, because they have different procedures. Actually, if you're in Louisiana Core Lab or Houston Core Lab, for instance. The goal of collecting this data, QCing this data, is to create an equation of state model for the entire basin. And the beautiful thing then is that when we've been able to create that, we now have a tool that allows us to go in to every single well in the basin and predict PVT properties with very minimal data. The minimum amount of data you need would be the GOR input right here, that we'll show a practical example of a little bit later. If you have the full-blown composition, you can also input that if you like. These equation of state models we like to refer to as so-called multi-sample equation of state models. That's what kind of Curtis Whitson, the founder of Whitson, I guess pioneered a little bit in the 80s. What it means in practice is that you have one model. So the two tables that Logan sent me earlier, these two tables with the comp properties and the binary interaction coefficients, they're fixed. They are not changing, but the composition that we feed into it is different. So when I change the GOR and everything earlier, I'm changing the compositions, but these two tables that is running behind the scenes here, they're the same. And you'll see that they're the same here because in the first part of the column here, there is no composition. And that's something you will see with a lot of PVT packages. They put the composition as a part of the equation of state, but it's not. It's an input to the equation of state. It's not a part of the equation of state, and that's an important distinction. The very clear definition of a multi-sample EOS is that each sample is described by the same EOS model, where each sample's unique composition is all that's required to predict that fluid accurately, okay? For that specific fluid. And what's different between a basin A, B, C, and D is how we characterize these heavy components. So we go back to this EOS model from the default in Whitson Plus here. If you don't have an equation of state, you'll see these components here, obviously up to C6. They'll always be the same. We talked about this. Molecular weight of methane is always basically 16 grams per mole. But everything from here and up, they have to be, all these properties must be estimated for every single basin that you work on, because they will be radically different depending on whether you're paraffinic or aromatic. Okay. So now we're going to go ahead and do an exercise together. After that exercise, we're going to take a quick break. And what we're going to talk about here is this practicability that maybe some of you have been thinking, okay, this equation of state thing is kind of good, but I only have pressure and temperature. How do I actually get composition, which is a very important input to this data? And in general, that's something we need to estimate with readily available data. Okay, so we have pressure, temperature, and composition. Once we have all this combined together, we can predict the phase and volumetric behavior. So, you know, if you talk to a laboratory, they would probably say, yeah, we need to go out and sample the composition or get a PVT report for this fluid. And if we did that, that would, you know, cost us 10 grand in sampling. It would take us a lot of time and send to the laboratory. Maybe they will even charge us, you know, $20,000 per year to keep the fluid stored in the laboratory. They'll write a 100-page report where we need to find a composition that we would like to use. Okay, so that's how it would look like if we had to do this for every single well through a laboratory. Okay, and the example here that I've provided in the handout is a public PVT report from Canada. Canada has all their PVT reports public. And that public repository of PVT data is also provided in the handouts. And I'll just show you that real quick right here. So this is not as bad in terms of number of pages. It's only 92 pages. Everybody sees that at the bottom here, 92 pages. And when it comes to finding a composition that you like to use, unless you have done this many times, you'll see that there's a vast number of compositional tables throughout this particular report. And you can see there's only 2 there. So unless you do this all the time, know what you're looking for, etc. And even then it can be complicated because you have different lab slates here, you have the isomers below the hydrocarbons, etc. So if you don't have the proper tools and if you don't do this often, it can really be a daunting task and like finding a needle in the haystack. So we need to have something that's much more, just in the appendix here, it's like 1 billion different composition tables as well. So this is just an example for you to take a look at if you want to. Okay, and this is not even a big report. This is for one fluid and Duvernay, I think. Okay, so finding this can be a needle in the haystack. So our job is like, okay, what can we actually do with the 99% of the wells where we don't have PVT data? And that's what we're going to talk about right now. And we're going to do a exercise on this, but I thought maybe we can do that. Let's do that together. Okay, so I would like everybody to go into their project, whatever your name is, just find your project here. And I don't know if maybe I don't have a project here. I have a little project here. Good. So once is everybody in the project now? So just find your project. If you go to fields, click fields, find your project, and then once you've found your project, you should see 2 wells right here. And what we'll just do here is do all the way up to the right. We'll just click add well, and then we can just call it your name or something. I'll call it Matthias testing. That will be my name here. Okay, and then we're going to do this exercise here together. Okay, so in your little project now, you should have 2 wells. These wells we'll look at later in the actual exercise, and then you'll have 1 well called testing, and that's it. Okay, so when you click testing, make sure that you go to PVT right here. Okay, and then at the top here, you should see the field Permian. You should be in your project. The well should be your name testing, and then just analysis should be main, and that's it. Are people following so far? Hopefully, maybe a thumbs up or something. But if it's too fast, let me know. But just again, in the project, make sure you're in your project. Add a well. The way to add a well is just to click add well here up to the right. Click make the name Matthias testing or whatever your name is testing, and then click PVT. And what we're going to do now is to use this readily available data to predict fluid properties. I'm going to go through all of these things together, so you've been able to click through this, and then later in the course we'll look at a real well and initialize this well based on what we see in the field. So the initial producing GOR that we'll start with is 1,000 scuffs per barrel. So what we're going to do here is to click edit. All these input cards right here, to open them, you'll click the edit icon up to the right. And then the method we're going to use is GOR. And then we'll make the initial total GOR just 10,000. Okay, change it from 1,000 to 10,000. And then we're going to click save. And what the software will go ahead and do then is to predict a composition that yields us a 10,000 scuffs per barrel fluid composition right here. Okay, so everybody saw that. You just clicked here, you used a method called GOR, and here you put in 10,000 and you click save. In the what you should also have seen is in the black oil table tab, you have already created the PVT tables for you. And you can see the tabular version of it if you like, and you can also export this table up to the right if you want to any third-party tools. But for now, we'll be in the fluid definition one. So this is a gas condensate well, and this is 10,000 scuffs per barrel. And here you also get the kind of formation volume factor for this fluid. Okay. The second thing that I would go ahead and do is like, okay, let's say we have an API measurement as well. We have, and now we're dealing with another well. So we're basically done with this well, but we're just going to use the same testing. And we'll change from GOR to API and GOR method. And we'll make the API reading 38, and we'll make the GOR 650. Okay, and then we'll just click save. So just again here, 38 and then 650. Okay, so 38, 650 right here. Okay, okay, it was probably 600. Let's make this 650. It doesn't really matter. My main point here is that you're able to use this other method, change to this other method. If you have an API number, provide that API number, and you can use the GOR and API combination to predict the fluid composition. The final result is still an estimate of the fluid composition right here. The tables are created automatically. The equation of state behind the scenes, still the same equation of state, but total different fluids, right? And later we'll go in and change this as well. Can people like give a thumbs up if they are able to follow, or is it too quick, too fast maybe? So that's the second one. There we go. So that's the second one. The third one method is if we have an estimate of our initial producing GOR, we also have an estimate of our saturation pressure. So now we're increasing the difficulty level a little bit. Another thing you should see here is that now what we have available is separator rates. So we have 1,250 scuffs per separator barrel. And we have a saturation pressure that we've estimated just from the field data we have when GOR starts to increase. We think that that's 3,000 PSIA. Okay, so that is that's what we're gonna look at now. Okay, so this is the saturation pressure, and this is a separated GOR. So now we're going to increase the difficulty a little bit. So we're going to change the method now to GOR and saturation pressure, and then we're going to put in a saturation pressure of 3,000. We're going to make the initial GOR 1,250. I think, if I remember right, 1,250. But we're going to make this a separator GOR. Okay, that means that we measure the rates here at separated conditions and not at stock tank conditions. Okay, we'll get back to that later. Okay, separated conditions. So when you have this is a little bit more computationally expensive method. It will take a little bit more time to run, but this is very relevant. And many times in the field, you'll see bottom hole pressures increasing and decreasing, and you see when GOR starts to shoot up from being fairly constant. That would be a good way, a practical use case of this particular method when you have that kind of data. Also, many times we have tests or we have rates measured at separator conditions, so then it can be really relevant to use the separator rates themselves when you do the initialization. Okay. The end result, though, is exactly the same. It is composition. It's different than these two other compositions that we had here and here. Much different. The classification is now a volatile oil, not a black oil, but the tables are generated automatically. The equation of state is the same. The amount of different components that we're feeding into the model is different. And now we can also see that we forced this to have a saturation pressure of 3,000. So now that's basically what it's been provided here in software. Yeah. So just let Mo know if you have any issues running any of these. Okay, so that's the third one. The only case that's a little bit special in Whitson Plus is if you have a dry gas case. So if you don't have any oil production, you would like to initialize your fluids, you would like to go down to dry and wet gas composition right here. And what we'll go ahead and do is that we will do a little bit advanced version of it. So you can put in the simplified specific gravity, that we'll do later. But now we're going to click dry gas composition right here. And in dry gas composition, we'll just put in 80 for methane. We'll put in 15 for ethane. And then for C3, we're going to put in 5. And C6 plus molecular weight, just put that to 90. It doesn't matter. There's no C6 plus. Okay, and once you're done with that, you just click Save and recalculate the fluid now. This should be fairly dry, I think, a dry gas composition, but who knows at this point. Okay, so that's the last example that we'll go ahead and do now. My main objective of this exercise right here is just to teach you that we have different methodologies depending on the data you have available. If you actually had a full-blown fluid composition available to you, then of course you could input that directly as well. Okay, so that's the last check here. We'll also take an example later of this separated composition examples, so we can actually do the Hoffman QC and the actual recombination directly in this interface if we would like to do that. Okay, yeah. Okay, that was the short exercise that I wanted us to all go through now. This we'll do just later in the exercise part. The last thing that I would like to show you is if we have a reservoir fluid here that we've predicted. I predicted this composition here to be, some composition up to C30 plus. I can actually take this reservoir fluid composition, and you see here, this is a black oil, bubble point is around 3,200. If I go there, input that composition in the fluid composition, I will get exactly the same results as what I already had right here. Okay, so that should give me exactly the same bubble point, same reservoir fluid. Now I just used a different method and not the GOR method. I think we should be good on that point. Okay, so that was just the exercise here, making sure that all of you are familiar with it. It's beautiful because there's so many things happening here. You're predicting the fluid composition based on readily available data. That fluid composition is calculating the phase envelope automatically. Automatically creating these tables that is used within the software everywhere where you need PVT as an input. And it can also be exported into any third-party tool with a click of a button here up to the right. Okay, very good. Yeah, I think that's the main things I wanted to go through here. Just while we're at it here, and I have all of you, before we'll take another 15-minute break, now it's a good point to just show you how to zoom these plots. Again, back to the certification. If you've done the certification, you've learned this. All of these plots are Plotly plots, and they will have the same functionality. So if you want to change the maximum part of the axis here, you need to go all the way up to the left of the plot or to the right of the plot here, depending on what axis you like to change. Or you can also do it down here if you like to. And you simply just left click once, and you see this blue thing popping up, and then you can just type in the number 10,000, for instance. Or you can go down and make it 5,000 if you like to. Okay, so you have to go all the way down. So that goes also here. If I want to make this negative, 1,000, you can do that here. You can do that here as well. So you have to be all the way to the end to be able to make these changes. Okay. Another thing is if you've zoomed in anywhere on the plot, you can click and drag and hold anywhere on the plot here. If you do that and you want to reset the zoom, you need to reset zoom up to the right here. You can do that. That's that button. That's the same in all the different plots up to the right. If you'd like to drag and drop the end of the axis, what you can do here is to simply just go to all the way to the top to drag and drop it, and the origin will stay fixed. That goes also down here to the right, and it also goes here all the way up to the corner here. The reason why we stress that is that if you're in between, that can be a little bit frustrating. If you're in between here and you drag and drop, then you're simply just moving the curve back and forth like this, and that can be frustrating. Last thing, second to last thing, is all the way up to the right here. You'll have the opportunity to drag the axis in an asymmetrical way if you're making sure that your cursor symbol looks like this. Okay, so that's important, that the cursor symbol will change when you're again going closer to the ends there. If you want to control the legends, the way to control the legends is to fast double click. If let's say the only thing I would like to keep on the plot is dew points, if I fast double click that, it keeps the dew point points there. And if I double click it again, I'll bring everything back. If I single click it, that's how I include or exclude things from my plot that's on the legend. Last thing, on every single plot, there should be a download button here to the top right, and that just downloads everything that is visualized on the plot to Excel, and that's it. So with that, we'll take a break. We'll be back at 10:15, and yeah, I'll just mute myself in a minute. We'll be back at 10:20. Sorry, 10:20. Okay. So we can start again. So now we have a little bit of background of what an equation state model is, which is great. And in general, we use that equation state model to create black oil tables or PVT tables for different engineering purposes. So that's the next topic. And just a reminder, PVT properties are a function of pressure, temperature, and composition. That's what we learned about already. So if you think about that, it's a very, very complex space, right? You'll have pressure and temperature, which is 2. And then depending on the number of components you have, you'll basically have a space that's 2 plus n minus 1 dimensions big, okay? So if you think about a super, super complex fluid with maybe thousands and thousands of isomers, you can't really think about how complex that space can be, if that makes sense. However, if we simplify this into 2 components, we're actually dealing with the black oil models, and those 2 components is a surface oil and it's a surface gas. Okay, so that's just plugging into this formula right here. 2 plus 2 minus 1, that's 3. So that's 3 dimensions that we can work in and understand. Okay, so that's what we're going to talk about now. And here it's important to emphasize that the black oil model can be used for all reservoir fluid systems, not only for black oils. So why is it then called a black oil model? Well, that's a great question. And the boring answer is that it's just a tradition. And it comes from the fact that when it was introduced, as a 2-component model, the oil in the tank, this was kind of before you produced condensates and stuff, the oil in the tank was always black. Then you have the other component, which was the surface gas. But probably a more proper name for the model would be the so-called 2-component PVT model. Okay, just remember that even though, like you'll see in Whitson Plus, no matter if you have a dry gas, it will kind of refer to a black oil table. Maybe a more generic name is like a PVT table. Our point here is that the model that you're using is sometimes or oftentimes called black oil, even though you use it for condensates and whatnot. So in a nutshell, if you summarize it, it's 2 components, surface oil and surface gas. There's 3 parameters for each phase. It's the formation volume factor, the solution GOR, and the viscosity. The solution, or the GOR. The GOR tells you how much it is of each phase, right? So that's basically the composition. The formation volume factor translated from surface to reservoir, and the viscosity is the viscosity. The model is dependent on surface processing. We did not talk about that yet, but we'll get there. So you'll see that there's 2 inputs here. It is the fluid composition and it's the surface process. And it matters whether we have 1 stage, 2 stage, 3 stage, etc. here to the right. To really understand the black oil model, we need to define a little bit of nomenclature, because it very, very fast here becomes a little bit, or it can be complicated if we don't have the correct subscripts. Okay, so when we're dealing with an oil reservoir, we can basically get, we'll have a reservoir oil volume. That's what we call VO. And then if we have any surface oil that's producing from the or originating from the reservoir oil, we're going to call that VO hat O. And then for a surface gas, we're going to call that a surface gas will be VG hat O. So that's surface gas originating from the reservoir oil. This was introduced by SBE back when they wrote the phase behavior monograph, I think. So this is SBE nomenclature. Okay. And you'll see why it's important that we distinguish between a reservoir oil phase and a reservoir gas phase. So for reservoir gas, the reservoir volume of gas is Vg, and if there's any surface oil or surface condensate, if you like, that originates from the reservoir gas, that's what we call VO hat G. Surface gas will be basically any surface gas originating from the reservoir gas phase will be G hat G. Okay, so to summarize this, when we have these definitions, we can go in and define these different properties that we find in a black oil table. And they are different whether you produce them from a reservoir gas phase or a reservoir oil phase. So from the reservoir oil phase, and where is this relevant? Well, it's relevant if you're below saturation pressure for an oil, or if you're below, which is the bubble point, or if you're below saturation pressure for a gas. You'll get these products produced. And if we start from the top, the formation volume factor for gas is the reservoir volume from the gas phase divided by the surface volume of gas originating from that reservoir gas phase. The solution CGR, also called the RV, is the surface oil originating from the reservoir gas divided by the surface gas originating from the reservoir gas. On the oil side, we'll have the formation volume factor is simply the reservoir volume of oil divided by the surface volume of oil divided by originating from the reservoir oil phase. And the solution GOR is just the surface gas originating from the reservoir oil divided by the surface oil originating from the reservoir oil phase. These properties right here, they're process dependent, which means that if I change the number of stages, the formation volume factors in these numbers will change. The last component in the black oil table is the viscosities, and they're process independent, so they don't care about the process. Okay, and just to convince you that this is true, here we see I use the reservoir fluid composition. So the reservoir fluid composition is the same. And if I go in here and add, let's say I remove a stage. So now let's look at formation volume factor and GOR and viscosity. Okay, so if I just do something simple here, just put them into a PowerPoint or something, so everybody remembers these numbers right here. And if I change to keep the reservoir fluid the same, but I reduce the number of stages, so I go from a 2-stage process to a 1-stage process, if that is happening, that means that these properties right here will change. Okay, so if I click save here, that will recalculate the fluid port as well. And what I should expect is for my formation volume factor and for my GOR to go up, okay, because it's a less efficient process. So I think my formation volume factor will go up and my solution GOR will go up, even though my composition is the same. My viscosity should be the same. Okay, so we take a look at this now. We see that both my solution GOR now went up. So if we take a look at this, a little bit ugly, but there we go. Viscosities here are the same. Solution GOR went up. The formation volume factor went up as we expect, but saturation pressure is also the same. And vice versa. If I add more stages here, so I think we had a 2-stage like this. So if I do, I don't know, maybe something like this, and add a 3rd stage, maybe that will reduce it a little bit further. The composition is the same, but the process is changing. Okay, so now it's 43.8, so that's a little bit lower. So now we made it a little bit more efficient, right? So that is a 3-stage process right here. Okay, so my point for you guys is that when it comes to PVT properties, they're these two guys right here, formation volume factor, and also if you're on the gas side, formation volume factor there and solution CGR, they're a function of separated conditions. A leaner gas condensate is much more sensitive than a black oil to these changes. But you see there's still differences here depending on your process. So having a relationship to what your process is at surface is very important when it comes to PVT properties. Okay, doc? Great. The different types of how they actually look like versus pressure, if you take the oil formation volume factor above the saturation pressure in what we call the undersaturated region, that's when the composition doesn't change. Your oil formation volume factors, they actually go down. The reason for that is that density also increases because the pressure increases. And then when you hit the bubble point, the gas is coming out of solution, your formation volume factor goes down on that remaining fluid. Okay, and that's what we call the saturated region. That's when we are within the 2-phase envelopes. That's when we are inside of this party right here. Everything in this region right here for this kind of fluid. Okay. So we're below saturation pressure. The solution GOR is constant above saturation pressure. So that's in the unsaturated saturated region. It's constant. That's when it's yeah. Just one. Give me 1 second. Okay, I'm sorry actually, Mo, you have to take this. There's apparently a bomb threat in the consulate here, so I have to leave the building ASAP. But yeah, so we need to take a break. Sorry about that.
Okay, everyone, so Mo will be ready in a couple of minutes, so just stay put. Okay, so we need a couple of more minutes. Matthias will set up everything at home, so we can take 7 minutes break until 40. That will be 11:40, and then we'll reconvene then. Thank you, everyone. That's 10:40. I'm sorry, 10:40.
Hey everyone, sorry about that. It's just a little bit unexpected, never happened to me before, but for those who don't know, I share, or the Whitson office shares office. We're on the half side of the building and the Norwegian consulate is on the other side of the building, and there's been some kind of bomb threat apparently that made the FBI and like a bunch of police cars, and there was a whole chaos there, so we had to evacuate. Luckily, I live pretty close to the office. I'm just doing the rest of the course from home here today. So just let me know if you can see my screen okay now. And if you are able to, okay, perfect. We see that. And sorry about that again. But I think we should be good in terms of time. As also Mo said, we'll be back at 10:40. So that should be 10:40, that should be good. So we'll just continue here if that's fine for everyone. Just continuing on these properties, these PVT properties on solution GOR. So again, we use this word undersaturated and saturated. That's just to describe whether it's in the region where the composition doesn't change or not. Again, saturated, that means that we're inside of the two-phase envelope, and here we're above it, basically, nothing else. Gas formation volume factors. Now we're flipping to the gas properties. The gas formation volume factor here is always looking like this. But in general, if you did the course with, I remember Curtis back in the heydays, if you really want to get the A grade, the B versus the A students, those were the ones that actually plotted the inverse of this, which is the gas expansion factor. The reason for that is like, especially this plot that you'll see here, the gas formation volume factor, the properties that you're actually interested in are kind of up here, and it's very hard to actually read what value that is for any practical purposes. So in general, at least when it comes to plotting these properties, we plot the inverse, which in bias B is just a small bg, so that's the gas expansion factor right here, and it's much easier for you to read. So that's why when you go into Whitson Plus, for instance, here in the software, let me just. In the software, you'll see that this is what is actually being plotted, and also the values when it comes to gas formation volume factor is not, it's printed in the table, but in the summary table, we're actually plotting the expansion factor. Okay. Any questions here? Or I think there's someone raising their hands, but maybe that was just an old. Hussein, do you have a question?
No, sorry, just my hand was up.
Okay, no worries.
I wanted to show a thumbs up. It stayed there, sorry.
Okay, no problem, no problem. Excellent. The other property there is the solution OGR value, what we call the RV. It looks like this. It has a shape that's constant above the saturation pressure, and then it decreases and turns non-monotonic in the saturated region. And to be able to understand why this shape goes up like this, a lot of people ask, is this a mistake? Yeah, just let me know if there's any question. Who has a question? Was someone? Is that Sarah? Sarah Leem, do you have a question?
Nope, sorry about that, Matthias.
Yeah, no worries. But I saw your text. Yes, it was what I said. But that's a good thing. Yeah, so this is just the unsaturated and saturated region. This is the dew point. That's when the composition is changing. And that's, in general, how these properties will exhibit themselves and show themselves on these plots. And they will be like this in general. So the shapes here should not be unfamiliar to you all if you use the software. Very fast on this shape right here that you see, the undersaturated and saturated region is or the shape that it goes down like this. The reason why it goes down like this can be explained with K values, and these equilibrium K values is what we introduced earlier today, and they're just a measure of the relative preference of a component to be in the gas phase or to be in the oil phase. So if this relative preference is higher than 1, it means that it likes to be in the gas phase, and if this value is less than 1, it likes to be in the oil phase. It's very simple like this. When it comes to the actual values themselves for components that are like to be in the oil phase or in the gas phase, those values are higher than 1, as you see, but they're also only relevant for a fluid system if there's 2 phases present. Okay, so that means that if you're dealing with K values in a single phase region, doesn't really make sense, at least from a physical perspective, because there's only 1 phase there. That would be, you would have a ratio of one of these guys will essentially be 0. Okay, so it's only relevant when the system is 2-phase, if you like. How they change these K values, they change as a function of pressure. So for low pressures in the low pressure range, and again, this what we're looking at here is for a constant temperature. So for a low pressure range, the relationship, if you plot the logarithmic value of K values versus pressure, they're linear, and the slope here is around 1, and they change as a function of the vapor pressure divided by the pressure itself. So the slope here is -1, so it behaves fairly nicely, if you like. But where it becomes complex, and where it becomes complex to model, and where these equation of state models become really important, is in this higher pressure region right here. So between, typically higher than 1500 psi, we'll see these values turn, call it non-monotonic, and they will actually converge at what's called the convergence pressure, and that's where all the K values for all the components are equal to 1. Okay, and this region here where we have K values that turn non-monotonic, or they are exhibiting this complex behavior, that is where you would need a complex fluid model like an equation of state to be able to model that. This convergence pressures, we get a lot of questions of, is that physically relevant? The only pressure at which it would be physically relevant would be at the so-called critical temperature. So if you're plotting this at the critical temperature, then the convergence pressure would be the critical pressure, and that's the only physical example of it. And this is a little bit complicated. However, if you understand these K values and how they change as a function of pressure, that's essentially what you're seeing, or why you're seeing these non-monotonic liquid dropouts, and also these non-monotonic solution CGR or RV curves and in the black oil tables. Okay, so initially, as you go below the dew point, let's say this is the dew point for this particular fluid. As you reduce the pressure will at some point hit or the components will, for most of the heavy components, the K values will go down, and then actually they will start to go up. And this period when most of them are going down, it turns into a net condensation region. And in this period when they go up, it turns into a net vaporization region. And that's essentially what you're seeing on the liquid dropout curve that we looked at earlier, and also when we looked at the RV or the RS curve itself. That's also why you have a condensation driven period and a vaporization driven period. And the vaporization driven period is when the RV curve starts to go up. So nothing else than this. This region right here is not physical, as we'll not talk about it. But obviously, pressure is above the dew point, then the phase is single phase. So it's only interesting more computationally than physically at that point. Okay. So now we'll soon do another exercise in relationship with the fluids in place. And that's a little trick that hopefully you have not seen before, but I'm sure that will help you to especially in these spaces where we have a wide range of different fluids, to get like consistent, continuous oil and gas in place maps. So we're going to talk quickly about initial fluids in place and a little trick that I'd like to show you all when it comes to fluids in place. So in short, when it comes to an oil reservoir, here you're looking at an oil reservoir with the formula for calculating oil in place. The formula for calculating oil in place is just a hydrocarbon pore volume divided by the formation volume factor. Very simple. So this stuff is just the hydrocarbon pore volume divided by the formation volume factor right here. And then the gas in place is just the oil in place multiplied with the solution GOR. So this is for an oil reservoir. Everybody knows this. This is what we learned about in school. pretty basic, just converting a reservoir volume to a stock tank volume and means a horizontal gas. For a gas reservoir, we've learned that it's a similar exercise. We do the hydrocarbon pore volume, which is this stuff right here. That's the hydrocarbon pore volume. And this is the formation volume factor for the gas phase. This guy right here, to get the oil in place, we actually multiply the gas in place with the solution CGR. So that's very standard. The trick here, and the trick that I'm going to show you, which makes it very, very convenient, I would say, is to start to use the concept of total formation volume factor and total GOR. And the reason for that is that it's really practical when you're dealing with these basins where you have a mix of oil reservoirs, gas reservoirs, and two-phase saturated mixtures. Because when you do that, you will then actually have to label the fluid first. Is it an oil? Is it a gas? Then go and apply the formulas. And also, if you wanted to do that for a two-phase system, it starts to become extremely complicated really fast. So if you use these formulas, you can use exactly these two formulas no matter what fluid type you're dealing with, even for gas condensates, for instance. Okay, and I'll try to explain you this. So it's an attempt to make your life simpler. So, and the way it becomes simpler is that instead of having to type in or label the different fluids, you can simply just use these formulas no matter what fluid type it is. Okay, and these formulas are automatically calculated, or these formation volume factor numbers are automatically calculated in Whitson Plus. You can export them out for all the fluids, and you can map out the entire basin if you like to. And it's just two values that you really should care about: the total formation volume factor and the total GOR. So what are these two, and how do you use them? First, how do you use them? Very simple. You take the hydrocarbon pore volume and you divide by formation volume factor, no matter if it's an oil, a gas, or a two-phase saturated system. You take the oil in place that you calculated and just multiply with this total GOR, no matter if it's an oil, gas, or a two-phase saturated system. And we'll take a look at this. But first, what is this total formation volume factor number? It's a little bit of a complicated, or not very complicated, but the formula is a little bit involved, if you like. But if we take a look at it, what does this thing simplify to? So if we have 100% oil, so the oil saturation is 100%. So let's ignore water here, but if it's only, at least in a split of hydrocarbons, if it's only oil, the formation volume factor, total formation volume factor, will be BO. That's what we should expect. If it's a gas condensate, the formation volume factor number would simplify to BGD over little rs. And BGD over little rs, that results into reservoir barrels over stock tank barrels, and that's what you would use for a condensate. Okay, so the units is what matters here. It's reservoir barrels per stock tank barrels. And for a two-phase saturated case, that's when your saturation pressures are higher than your initial reservoir pressures. Then the total formation volume factors will represent the saturation-weighted oil formation volume factor. Similarly, on the GOR side, the total GOR, once a fluid is an oil fluid, it will simplify to RS. And when the fluid is a reservoir gas, it will simplify to 1 over little rs, and little rs is just, it's just barrels per million, so this will be then scuffs per barrels if we do the inverse. And for a two-phase saturated case, the total GOR will represent the saturation-weighted GOR. And again, how you will apply them, it's just these simple formulas. You calculate hydrocarbon in place, you get that from your petrophysicist, and you just go in and apply these no matter if it's an oil, gas, or a two-phase system. The only exception is if it's a dry gas system. That's the only thing. As long as you have liquids, these formulas are perfect. So our exercise now is to be able to go in. I want all of you to do this exercise now for a case where we have a hydrocarbon pore volume of 5 million barrels. Okay, so 5 million barrels. And I would like you to, for this oil case, this gas condensate case, this is like a 100 barrels per million case, and in this two-phase saturated case right here, I would like you to go in and calculate the oil in place and gas in place for these different scenarios. So that will be a quick exercise now, and I would like everybody to write that just quickly in the chat, the numbers that they come up with. Okay, so just for the oil case, the gas case, and the the two-phase case, can we come up with the oil in place and gas in place numbers? Yeah. Just X, Y, Z on these. I'll give everybody a couple minutes for that. And again, the formulas can be found in the slides on a couple of slides back, right? So that's on slide number 121. That's the formulas you'll apply. Just hydrocarbon pore volume divided by formation volume factor. That's the formulas we should use. Okay, have people been able to do the calculation? Should be fairly straightforward. You do this calculation, you'll end up with something like this. The first case is just the hydrocarbon pore volume divided by 1.93 gives you this, and then you take this number and multiply with the total GOR. That's the RT. Then you do the same thing here in a similar manner, and the same thing here in a similar manner. And these numbers right here are automatically outputted when you use Whitson Plus. So that's nice from that perspective. Any questions about this this exercise? Hopefully that was straightforward. Second to last topic we'll cover before we'll do the final exercise of the course today. That's going to be most of the clicking today. It's going to be these black oil table generation topic. It's a little bit of an advanced topic, so just bear that in mind. But in short, these tables that represent the black oil model, that's what we use all the time in all the different softwares that we use, whether we like it or not, whether it's actually given to us or not. It's typically represented by tables. These tables, they exist they have typically 7 different columns: the pressure column, and then the 3 properties for each phase for the different pressures, and then they have or they're always generated at the constant temperature. Okay. They're used for reservoir simulation purposes, RTA, PTA, pipe flow, process, and facility design, and much, much, much more. The things that's required to create a black oil table is what we're going to talk about here in this session, but you need an equation of state, you need a temperature, you need a composition, and you need a surface process. And that's the 4 things that's really required to create a table. And that's it. And in the software, you have the equation of state, you input a temperature, you're using, for instance, GOR to predict composition. And then we looked at that just before this bomb thing happened with the surface process, right? That we changed the surface process, and that's also an input to creating the tables. That will change your PVT properties. So just real quick, it's a 2-component PVT model. There's 3 properties defined for each component. The one important, it's more like an FYI to be honest, but one assumption that you're making in any PVT table is that the surface oil and gas densities are assumed to be constant, and they're assumed to be the same whether they come from the reservoir oil phase or the reservoir gas phase. So if you're dealing with a gas reservoir below the saturation pressure or an oil reservoir below the saturation pressure, and you're flowing 2 phases, obviously those 2 phases won't exhibit for instance, a reservoir or a surface oil with the same densities, but that's an assumption that we're making. Is it a good assumption? Yes, it's a really good assumption. It seems to work very, very well. And if you're creating PVT tables from an equation of state and you do that consistently, at least for primary depletion, you'll get line thickness the same results as if you ran that model compositionally. The only times you will need to run it compositionally would be for gas injection or compositionally sensitive processes. And the last thing is that the PVT properties are process dependent, and of course that you're assuming that the temperature is constant when you create a table. So if you use tables for instance, pipe flow calculations where the temperatures are different, you actually need to create a series of different tables that you interpolate within. Okay. And this one we looked at already, but this is just to emphasize this thing, what properties are process dependent and which are process independent. So what can you optimize on surface, if you like, and that's the volume related properties. And again, that's going back to the fact that, why do we talk about separator optimization? Why do we use 3 separators versus 2? What's the incremental value out of using or buying another separator on site versus just having 2 or having 1, for instance? And that's related to that it actually matters for how much liquid we're able to resolve from a given hydrocarbon, call it composition, versus if we do one process versus another. And this also goes back to that context item we talked about, that 1 cubic meter is not always 1 cubic meter. We repeat that because it's important and it's very fundamental for the whole PVT concept. And again, these black oil PVT properties are a function of surface process, just not the viscosity. So in the background, when you click, generative, or you're using the PVT feature, for instance, in Whitson Plus, you predict the composition, and you're automatically generating these tables. What is actually going on behind the scenes is that you have an equation of state model there. You input a temperature. You predicted the composition with one of these methods. You have inputted a surface process, and then one additional item you need to do is to assume a depletion process, so like a PVT depletion process, whether that's a CCE experiment, a CVD experiment, or a DLE experiment. In general, what we use automatically in the software is assuming a CCE experiment. That's what also Sensor does and some of these other simulators. That is what we've found to be working the best in general. You should be okay with the CVD as well, but the DLE is really not a good choice there. So, but that's not an active choice that you can change in the front end. That's a choice we've made for you, and it works excellent in general. So when it comes to the tables and how they look like, 40 years ago, the tables actually looked like this. They were missing a component. So they assumed that back then, traditional black oil tables, that all the gas in the reservoir was dry, that they could not have any condensate in solution when you produced it at surface. So you had only 3 components for the oil phase, and you had 2 components for the gas phase. That's what's called in traditional black oil table. I'm a little bit shocked that softwares still allow you to use these tables because they're always incorrect, and it's not like this big computational issue to include the additional component there. So you just make, so when you for instance make the difference between a black oil and a liquid rich type of system in softwares, it's typically the difference of assuming that it's like the reservoir gas has condensate in solution versus not. But do not use these tables in general. If it's not important, just the RV value will be very low and the amount of gas will be really small, so it won't really matter. So in the 80s, they introduced these modified black oil tables, and these modified black oil tables will have this RS term or this RV term right here. And the formation volume factor for gas would be dry, so to assume that you had removed anything that becomes wet at surface, okay? And this is what you are generating by default in Whitson Plus automatically. It's also what we recommend to use in general. That is what is correct, and it's also what is required for you to have a model that's giving you exactly the same results compositionally as in an equation of state model if you generate the tables consistently. And of course, for all these different undersaturated parts or all the saturated parts of the curve, you also will have an undersaturated part of the table that we just plotted on here. A little issue is if you have this table right here, and if you generate this table, it has around a solution GOR of 2000 there. But let's say after we created this table, my great friend here, Sarah Leames, for instance, she says, maybe the in situ representative GOR for this well is not 2000, it should be maybe 2500. The problem here, though, is that we would not have a composition with a solution GOR of 2500. So what was also introduced probably around 2000 was this concept of extrapolated tables, extrapolated black oil tables, that would essentially take your fluid from whatever the saturation pressure is and extrapolate it up to typically what's called a critical point right here. And the critical point, that's the critical point, the same one that you saw in the phase envelope, it means the same, and that's just when the properties of oil and gas converge. So at the critical point here, the viscosity of oil and gas will be the same. So this value right here and this value here is the same. The solution, if you plotted this in GOR space, they will be exactly the same right here. And also the formation volume factors will be the same if you plotted BO versus this BGD over little rs term. They will be consistent and the same at the saturation or at the critical point. So that's also something that we extrapolate at least some of the tables a little bit, such that you can still play a little bit around with your GORs. You don't have to update it in the software. So if we think about reservoir fluid classification that we discussed earlier, but in the context of these different black oil PVT properties, we can come up with some rule of thumbs. And again, these rule of thumbs are just estimates. It's not something we should interpret as absolutes. But a black oil fluid would typically have a BO less than 1.5, a GOR less than 1000. A volatile oil would have a BO between 1.5 to 2.5 and a GOR between 1 to 3000. Near critical fluid would probably be between 3 to 4000. A condensate can have a really big difference in terms of range. The so-called formation volume factor, if you like, that's just to make sure we get reservoir barrels per stock tank barrels, will be 4 to 50. And it can go from 4,000 up to 100,000 scf per barrel. And then we have a wet gas that can have still a so-called formation volume factor and a very high GOR. And of course, when it comes to a dry gas, it has no formation volume factor and no, for at least like an oil formation volume factor and no GOR. Okay, so that's just a little thing. Again, these tables can be used for all reservoir fluid systems, and I think this is an example of that, so just keep that in mind. The last slide we'll do, and then we'll take a break, and then we'll go into exercises. The last thing there is the reservoir water. The reservoir water, if you want to change that in the software, in the fluid initialization box, you can click this little droplet symbol, and you can change the water salinity from being 0 to whatever is relevant for your reservoir. Water is a little bit less complicated to model, but there's a couple of things from a PVT perspective that you should be aware of. those things is that the water viscosity typically ranges from 0.3 centipoise to maybe 1 centipoise, depending on the temperature. If it's very high temperature, it can be probably down to 0.3. Then as you go up to ambient temperatures, you can reach probably 1 centipoise. The compressibility of water, it's not very compressible. So that's between 2.5 to 5, 10 to the minus 6, and then just 1 over psi as the unit. It doesn't really shrink much, very low shrinkage when it's produced to surface. That goes back to that, there's very little things in solution with the reservoir water, and it's also not very compressible, so it shouldn't shrink a lot, typically much less than 5%, maybe 1 to 2 most times. And the only thing is that when you have brine that is sharing pore space with hydrocarbons, that brine will always contain small amounts of gas in solution. Okay, so and that will be mainly methane, so ranging from 10 to maybe 35 scups per barrel. And that's something to think about for especially some of these areas where we produce a lot of water. If that water has been sharing pore space with hydrocarbons, some of the gas you're producing at surface, especially if you're in we have your water oil ratio is like 5, or your water cut is like 80% and stuff, or 0.8. Some of the gas that you're producing will probably come from the water phase. So that's just a little FYI. So with that, I'll just take a little break, and then we'll come back and do an exercise, and we will be back in. Let's just make that 10 minutes so we can make sure that we're able to run through the exercise, all of us together. So we'll be back at 11:20. Okay, 11:20. Okay. So we've got a few questions related to the some people for their petroleum engineering points or training credits or whatever it's called. If you need like a kind of a course certificate or anything, just send me an email and we'll get that sent out to you ASAP after the course today if you need that. What we're going to do now is just the last bit, which is the exercise piece. This will be with some real data that we have uploaded in your projects. And we're going to go through just the PVT part, play with a few different items, and also make sure that we know when we're going to use certain features versus other, if you like. So in the exercise piece, the first thing we'll go ahead and do is to go into our project. We're going to pick the first well here in the project called the kite well. And again, if you're unsure how to find your project, go into project here up to the left and just find your name. You should only have one project there, and this is what you should see. And once you're done with that, we'll click the first one, just this SB repository well right here. We'll go to the PVT step right here, which is the first one. That's where we're going to do most of the work. Okay. And to do the PVT, whether it's this well, a synthetic well, if you have production data or not, the only place to edit and change your PVT is in this interface right here. So on the reservoir fluid composition, we'll click this edit reservoir fluid composition. And every time when you have uploaded production data, then you get this interface right here that shows the gas oil ratio. And for this well, we've uploaded some production data for you. That's what you're seeing here. And automatically you're zoomed in to the first 100 days. And then we go below saturation pressure, and we've got a lot of complex phase behavior happening later. Okay, so your job is to take this line right here, this dashed line, or you can also type in a number here. You can type in 750 and then tab out, for instance. Then that changes. So if I made this 2000, it changes. You can do both. What I want you to do is to try to find a stabilized portion of the data that you're happy with. This is after the well has cleaned up, and it kind of stabilizes here around 770 or something like that. You can also, if you'd like to, zoom in on this even more if you want to. And once you're happy with that, you click save. Okay. So that's the first part of the exercise. Real data, when real data is there, that will be your best friend. You just drag and drop this line to match the initial producing GOR when we use the GOR method. Okay. For this well, we have then predicted a saturation pressure of around 2,900, depends on what you picked here. Here, maybe the engineers will do a little bit different interpretations depending on who it is, but that's how you initialize your fluids. That, as I mentioned before, automatically generates this black hole table, but it is the same equation of state that is being used. What I'd like all of you to do now is that in the reservoir fluid composition card, there is this view fluid composition. So if you click this this button, you can see the reservoir fluid composition right here. And if you copy this, you can bring this into, for instance, Excel. And that should just be for you to copy paste this into a blank worksheet like this. Okay. So everybody saw that. You open up the reservoir fluid composition, whatever you call this, view fluid composition, this eyeball symbol. Someone has a better name for this, let me know, but I call it an eyeball symbol. And you see the components here all the way up to C30, and you can copy these into Excel with a click of a button like this. What we see here is for this, since this is a default equation of state, there's in the, call it the seed feed tables we use in the background to make this prediction, there's no non-hydrocarbons, so we'll set some of the non-hydrocarbons now in a sec. Okay, but this is how you basically can see the reservoir fluid composition that you've predicted. That's in situ representative, right? So that's what your interpretation is that that's an in situ representative GOR, and this is your best guess of that for this particular well. Good. The next thing we'll go ahead and do is just specify the non-hydrocarbons. So let's say we have some information about the non-hydrocarbons. we can go in here and set the non-hydrocarbons right here. And here it's really important for you to make sure that you have an appropriate zoom in your browser. And the way to zoom your browser here is to do just Control+ or Control-. That's the only thing you need to do. And in this reservoir fluid composition card, you can then set the non-hydrocarbons, and they can be 0.5 and 0.7, and then the last one is 0. Okay, so once you're done with that, you click Save again, and then we recalculate our fluid, and that's basically step number 3 here. Okay, and if you check your reservoir fluid composition again now, you should see that your components right here that you inputted, they are being reflected in the for this particular well. And you can then go in and copy and paste that into Excel as well, and you can compare these two right here. So now we have the non-hydrocarbons as well. If there's any questions as we go along here, or maybe I go too fast, let me know. Okay, so we've done 3 things now. We've been able to drag and drop this line. We've been setting the non-hydrocarbons, and we've run the compositions twice, and that's where we calculate these tables. Yeah, and we've checked our compositions as well, so we see that the compositions have changed. The next thing I would like us to do is to go in and check what our saturation pressure is for this fluid. Here you can see what the saturation pressure is if you just hover over the initial pressure, and you'll see it's around 3,000. The actual value, much simpler to do, would be to go in here and actually read the actual value here to the right. And I'm pretty sure now we're probably just a bunch of people running it, so it takes a little bit of time for the system to update, but that's where we'll find it under the black oil table right here. So we'll have the second tab right here. The bubble points should show in this particular table. So that's where you find the reservoir or the saturation pressure for your predicted fluid. Yeah, so this takes a little bit of time. I think everybody's following so far. So that's step number 5, probably around 2,900. So what I would like us to do now is that if we have a fluid where let's say we've been looking at the saturation pressure, or just the bottom hole pressure versus GOR really. Let's say we go into this well and we actually see, okay, here after around, I'll just zoom in here, 200 days, we see at around 100 days to 120 days, something is happening with our GOR. So it starts to shoot up here. My interpretation could then be, okay, here we're around 3,000, and I'll say my saturation pressure then is maybe 3,000. Let's say that that's my interpretation for this well. So then I can go in and say, okay, I would like to go and use the GOR and saturation pressure estimate such that I've been modeling what my saturation pressure is based on that observation. Okay, so I'll put in a GOR now, and I have a saturation pressure estimate, and now I'm basically forcing my reservoir fluid composition to exhibit a saturation pressure of 3,000. So that's the part of the exercise that we'll go ahead and do now. So to do that, just change the method to GOR and saturation pressure, and once that is done, you just change it from GOR and saturation pressure, and then you change this value to 3,000. So you're done with that, you click Save. This method is a little bit more computationally intensive. So while the other ones take 2-3 seconds, this probably will take 4 or 5 or probably 15 seconds or something, 15 to 20 seconds, because it's a little bit more involved computationally. We run literally hundreds, maybe thousands of flash calculations when we're actually doing just one quick predictions like this. So it's very automated from that perspective. So maybe it took 15 seconds or so. The end output, however, is the same, right? It's a composition now that we have up to C30 plus. We have automatically created this phase envelope for us right here, and the tables is also generated automatically for us. And now we see that our bubble point is forced to be 3,000. So if I went in and used this model in my numerical model, I know that when I go below the saturation pressure of 3,000, that is when GOR will start to increase, right? Or at least that's when gas saturation is starting to build. So this is a really popular method. A question we get many times here is like, okay, should I use the GUR and API method? In the beginning, I was a big advocate for using the API and GUR method if you had a liquid API number. The problem in practice is that the liquid API numbers you get from the field are typically very uncertain, and typically they are produced through a very different process than your total GUR number that comes from production data. You know, there might be just simple uncertainty in the measurement or how long it's been exposed to air. So in practice, the API and GUR method, I've kind of gone away from using. So either well, at least my recommendation is to use the GUR method. And if you have a saturation pressure estimate, I would use the GUR and saturation pressure estimate. Obviously, if you have more information than that, like the full reservoir fluid composition, you can use that. The thing we're going to go ahead and do now, which is a little bit fun, is that we're going to create a synthetic PVT report. So based on this fluid composition that we have and the inputted reservoir conditions, we're going to go down to virtual PVT lab, all the way down to the left here, and we're going to click simulated PVT study. And in simulated PVT study, there's a big button called generate new PVT study. Okay, so we went from all the way up here down to virtual PVT lab, and we expanded that, and now we're ready to click generate new PVT study. Okay, once you click that, what happens with the software is that the software automatically creates a PVT report for you. This is the summary of it. We see the CCE, we see the DLE, we see the multi-stage test and the viscosity test, and you can see from, for instance, the CCE experiment, what the saturation pressure and whatnot is. But for you, if you're interested in taking this report, exporting it right here, saving it, you'll actually see that this is very, very similar to what you could get from a PVT laboratory. Maybe I will just do something like this just to show it a little bit nicer. Enable contents, and what you'll see there is we have a front page. You can even print it by clicking this print button right here. So I'll just that, maybe that looks better. And then yeah, I think I had two of them. But the front page, the fluid analysis page, all this summarizing the predictions for this particular fluid, multi-stage test where you get your formation volume factor, the compositions in mole and mass, the CCEs, the CCE plots, the DLEs, you name it. Many of our clients are using this in communication with you know, for instance, the Texas Railroad Commissions and equivalents. They use it to talk to other non-operating owners for a field or for a well. It can also be nice to just, if you want to do a quick QC, just to check for similarities in saturation pressures and stuff between a laboratory measured report and the equation of state you have uploaded for your field. So it has just several different use cases that I think could be nice for you all to know about. So again, go down there, simulated PVT study, generate new PVT study, and we are off to the right system. You export it up here to the right. The reservoir fluid here is for this well, we learned about the liquid dropout. So obviously this is a black oil, but you can also see that in the liquid dropout for this guy, that it's more of a linear type of relationship when you go below saturation pressure, and it's not really curvy. So that's also another indication that we're dealing with more of a black oil in this case, and it's also what's being predicted by the system right here. But again, you know, black oil, volatile oil, it's primarily labeling, not much else. So if we take an example again here, just assuming a hydrocarbon pore volume of 10 million barrels. Oh, that should not be MSTB. Sorry about that. That should be RB. That's my mistake, rookie mistake. But here we are, RB. Sorry about that. And if we take a 10 million reservoir barrel well, and we start to calculate the formation volume factor, or we use the formation volume factor and the total GUR to estimate the pore volume, we get what? Okay, so you go here. These are these numbers that I talked about with you all. The the total formation volume factor and the total GOR. These are the numbers you can use in all the different cases. And when you go into a project, you can go in and actually export this for all the wells in the project by clicking just export selected, and you get a summary of all of those properties, the compositions predicted, etc. So you can map out these properties very nicely in the software. And in the future, we'll also be able to map that out directly in Whitson Plus as well, which we'll get to. But just for this simple exercise, just go in and calculate what the oil in place and gas in place is. If we assume a 10 million barrel well, so that's 10 million reservoir barrels. So take 10 divided by 1.382. It gives me 7.2. So I think that's 7.2. Hopefully that's correct. And if you take 7.2 and you multiply with 750, you get 5.4 BCF. Okay. So yeah. So something like this. So this is the answer that we have down here. Okay. So hopefully you get the same. Important for you all is like when you calculate these maps, if this was a condensate well, if it was a two-phase saturated well, you know, you can still use these values. And I'll show you just unless there's any other exercises here. Yeah, now you can go in and export this into Excel, for instance, if you want to take a look at it there. And when you export things, that's being generated in the backend. Then all the overview of the files will be given here in the generated overview. So I have them over here, and that's the place where you can look at the table in Excel. But it also has the exports to any other tool that you might be using right here. So export is up to the right. Eclipse, Kappa, Harmony, IMAX, ResFrac, T-Navigator, Excel, Sensor, Powers, Prosper. Okay, so it has a lot of different exports there. And you can also look at it in tabular form, and be able to copy out the BOT here to Excel. So that's more of an FYI there. And for those that are really interested in the Excel sheet, there's some hidden secrets there. So if you want to be a Whitson power user, you'll know about the unhide part of the Excel file. That, for instance, can show you the GOR advanced plot. And what, yeah, that's my bad that I have a big little bad format on my computer here on the small screen at home. But there you basically see an extrapolation portion of the table from that we talked about initially. So we have a little portion of the table that is extrapolated above the saturation pressure. Very good. The last thing I wanted to show with regards to this before I go in and run, okay, let's do one last thing, just simple material balance calculation. Again, if you have an estimate of what your abandonment pressure is and your total GOR is at the end of history, and you have a fluid initial conditions, you have what's required to calculate a simple material balance. So you go all the way to PVT, simple material balance. Here you put in an abandonment pressure of 1,000 and just a cum GOR of 5,000, I think is what I put in. Okay, so if you do that, the software will go in, run a calculation for you, and predict some recovery factors if that's what's true at the end of history for your well. Okay, so this will be the absolute upper minimum, upper maximum. Just simple material balance. You will get the same results if you put in this into the numerical model, or if you put it into, for instance, the Multiphase FMB workflow in the software. But this is a very fast way to just get some numbers if you're interested in that. So that's also here. That's just PVT and an estimate of abandonment pressure. That's it. So to input the abandonment pressure and GOR, you just do that here in the software. Okie doke. So that's number 9. And we're going to flip to the dry gas well now in 1 second.
Matthias, could you run that again? We have a comment on the chat.
Will you run through that again? Yeah, perfect. So if we're in the PVT part here, you go from the PVT part all the way down to simple material balance. That is down here. And then in simple material balance, we have the material balance input. And in the material balance input, we just edit right here. And you input the abandonment pressure and the cumulative producing GOR. You click save. And once you've done that, now we want to recalculate here, or yeah, we probably will get a recovery factor of around 9% for oil and for gas around 60 for these assumptions. Is that okay? Perfect, Justin. Thank you. Thank you. Awesome. So that's
about cumulative producing GOR. Is that GOR at abandonment?
Yeah. So that would be the cumulative producing GOR. That would be the cumulative producing GOR at end of history, basically, when you abandon the well. So that would be associated with abandonment pressure. Exactly. So for people doing, for instance, decline analysis for a well, you know, implicitly, if you have a decline, you have also a cumulative GOR at the end of history, because you have a decline on both oil and gas. So you can take those cumulative GORs at end of history, plug them in here, have some educated guess based on abandonment pressure, and you have everything you need to calculate recovery factors. And these will be the upper limits of recovery factors if your entire tank size actually reached that abandonment pressure. So it's a good kind of exercise to go through to see if your forecast makes sense as well. I wanted to show here is this, you know, I'm stressing this thing about these formation volume factors here, these BTs and RTs, that they are really helpful. For oils, they're the same as BO. That's fine. But what if I change my pressure now to go down below the saturation pressure? Let's say I make my reservoir pressure 2,500. What actually happens then is that now I'm already inside of the two-phase party. This happens very often in places like the Scoop Stack and in the Montney, for instance. You have also parts of the Permian with this characteristic. So you have saturation pressures that are above the initial reservoir pressure. So you're already in the three-phase party already. So then you will have a oil phase, and your oil phase will have a formation volume factor and a GOR, and you'll have a gas phase with the same attributes. So if you wanted to do that, like a consistent map of the whole basin there, it would be super complicated. But here we have the dream for you here. Just get the hydrocarbon pore volume, divide by BT, that's your oil in place, and you use the total GOR here. So that's how you would use it for a case like this. And if this was a gas condensate well, I'll just show how that looks like. For a gas condensate, you'll still use the total GOR value, and the total GOR will just be that BGD term divided by the little rs. And that will give you this formation volume factor of 12.7. That's just this is a gas condensate. There's a low, let's make this 8,000 just for example. This is just to show you guys. Okay, I need to do a couple of things here. Just give me one sec. There we go. So for this case, gas condensate, it will have a much higher formation volume factor, 6.2-ish, but you could use it exactly the same way. Okay, that's the same units. Typically, it's a number higher than 4, and here it's for a condensate with 100 barrels per million. So really practical for that if you are transitioning multiple different fluid windows, if you deal with a lot of air critical fluids, etc. It's very practical from that perspective to use these two numbers. And to get them, you simply just go to wells, you click or you select all the wells in the project. In this case, it's only one that's really relevant. So you can click here in the wells overview, and you click export, and then you get the data for that one well. And then there you actually get all the data for the well out in an output file. You get all the completion metrics, all the inputted parameters, and at the end here, you should get all the fluid data. So saturation pressure, formation volume factors, GORs, you name it. And many of you know about this, and we've helped many of you to create these maps. If you have not done it, let me know. I'll send you a few case studies of how this is used internally in some of the companies. We'll do now. See, we're running out of time, but that's perfect. The last thing is we'll look at the dry gas well. So we'll flip to this other well by going into your well overview, go to the one called is it peasant or peasant? Yeah, anyways, this well, we'll go into this well, and we'll look at the production data here. And here we see there's no oil. The oil is 0, essentially. So this is a dry gas well, and for dry gas wells, we have a little bit of a special thing on the PVT side. That's that we go into PVT, and then we change the methodology from GOR, which is the default, to the dry and wet gas. And if you upload this through the API connection or the mass upload version, of course you can do that automatically. But in the front end, if you do it manually, you have to change it to the dry wet gas method and input a specific gravity. So that's the first thing that we'll go ahead and do. We'll input a specific gravity of 0.6. We'll click save. What we see here is that it's so dry that we don't even have a phase envelope. That makes sense. So that's fine. We'll also go ahead and make an example here where we provide our non-hydrocarbons. So that'll be these guys right here, 0.5, 0.7, and 0, I guess. Click save. This is exact same exercise. The only thing now is that we'll get our non-hydrocarbons here. You see it's primarily still methane and none of these very high, heavier components that make a phase envelope right here. So this is very, very, very dry stuff. That's the main thing to be aware of. In the so-called black oil table, it's still called the black oil table, but this is only gas properties here. You see that your RV is 0. There's no gas in solution, so that makes sense. It's a dry gas well. We don't have any solution GOR, so it's just a reservoir gas density, gas viscosity, and a gas expansion factor, and that's it. So this is a so-called dry gas PVT table. Okey-doke. The absolute last thing we're going to do is we're going to take a. We can take this well right here. I'll just show you all how this is done. You don't have to do the same thing, but I'll go to the sampling data right here. This is a link. This link will download some data. Just an example of separator data. It's very common in a lot of basins where you have separator sampling data. It's very, very inexpensive to get this data up to C7. That data is very nice because now you have resolution on your non-hydrocarbons and also some of these lighter hydrocarbons. So it's a little bit more rigorous exercise when it comes to predicting the components. That methodology is the method called separator compositions here. And you can simply just take that separated gas and separated oil from this one, copy it into this one, up to C7. We have a separated GOR that we input here. Pressure of 200, separator temperature of 120, and then a 99 specific gravity. 175 molecular weight. What we also see now is when we click normalize, we get this Hoffman QC. Here it looks like these are not really in very good equilibrium, at least not this guy right here. And that's very common that we see some of these components with very little amount of N2, for instance, in the separated oil, and vice versa, that they can cause some big deviations. Doesn't necessarily have to be a problem, but the point here is that when you do this exercise and you click save, it's exactly the same type of exercise. We use the equation of state. We use that to predict the composition. That composition is up to C30. So there's inbuilt what's called a gamma model that splits this C7 plus up to C30 plus. That gamma model was kind of why Curtis Whitson, our boss, Curtis, got kind of known in the 80s for the first time for his PVT work and contributions. So that's what's being used. That's also developed as a part of all of these consortiums. Every single basin has a little bit of a different gamma model, and this is just an example of it. But this is a different method, same end result. You get a composition. Composition creates a phase envelope. That phase envelope creates the tables automatically, and you're off to the races doing everything else that you would like to do in the software, or if you like to do export this into a third-party tool, that's also 100% fine. Very good. So I think that's actually the last piece here. I think on time it went okay. I got a little bit stressed there after this whole thing, but I think we were okay on time. The last 10 minutes, we'll just have, if anybody has any questions, feel free to ask them now. Else we'll just end the course 10 minutes early, which I think would be fine as well.
Matthias, I just have a quick question there, if I can ask.
Yeah, perfect.
Yeah, perfect. Even though we are just so these EOS models are being built, using tons of data, and there's much more confidence on that. But down the line in our asset, if we are acquiring some of the lab data in terms of CVD, CCE experiments, and we want to fine tune some of the values that we get from the PVT study section here. Is it possible, or it's not possible right now?
Yeah, good question. So what and that happens many times, that you get more data, you would like to verify the model towards the data, and that's stuff we do for all these different studies multiple times a month, actually, for different operators. So the workflow for that is exactly the same as if we were almost developing it from the get-go. You take the data, you QC all the data in the report, make sure that all the reports are good quality data. If there's any bad quality data, you just weed out that. You don't weed out the entire report. Make sure that the compositions are good. There is no bogus there. And then you simply just do a verification of that the model that you have already is doing an excellent job on predicting the different PVT experiments. If that's not the case, then you would probably like to update or retune it. So that's something that happens from time to time in the consortiums that we have, and then we provide an updated model to everyone that we distribute. Okay. Yeah. So that's how it works on.
Okay.
That's happened before. Yeah.
Okay. So yeah. Okay. Thank you. Thank you.
Awesome. Any other questions, everyone, or is this? Okay, sounds goody. So with that, we'll just end it now a little bit early. If there's any questions, always feel free to reach out to support@whitson.com. Happy to help whenever. Also, the material will be sent out once again after the course today. Should have been provided already as well. Thanks all.
Thank you.
Thanks, Matthias. Appreciate it.
Thank you.